It's wonderful to have you here. Tonight we'll be looking at something that stretches across billions of stars, billions of years, and an unimaginable amount of empty space, and yet arrives at a question that is unsettlingly simple. Why is the universe so quiet? Just a little favour to ask before we begin. If you have a moment to spare, I'd really appreciate it if you took a look at our ebook over on the Sleepy Scientist website. It takes the ideas from these videos and gives them room on the page, unhurried, laid out with all the space they need to properly settle in the mind. The whole thing is narrated too, so you can read it or simply listen, and at the close of each movement there's a short quiz waiting, a gentle way to see what's stayed with you, and to turn the ideas over once more before moving on. The QR code is up on screen, and there's a link in the description to the sleepyscientist.com whenever you're ready. Every reader who takes a look is the reason these videos keep appearing, and to anyone who takes the time to buy it, I don't think you quite understand how much that means. That's the only ask tonight, and thank you sincerely. Now, I'd love to know where in the world you're watching from tonight. Perhaps you're listening from a quiet bedroom, curled up on the sofa, travelling somewhere in the dark, or settling down after a long day. Wherever you are, I hope you're comfortable, relaxed, and ready to let your thoughts wander for a while. And if you enjoy these calm journeys through science, a like and a subscribe are always appreciated. The Milky Way holds billions of stars, many of them far older than the Sun. Planets appear to be common, and some worlds may have had billions of years longer than Earth to produce life and perhaps technology. So if anyone else is out there, where is everybody? This is the Fermi Paradox, and tonight we'll explore the Drake equation, the Great Filter, the Rare Earth hypothesis, the Dark Forest, and the possibility that alien intelligence may simply be too distant, too quiet, or too unfamiliar for us to recognise. I'll do my best not to make the silence of the cosmos sound too dramatic, though the universe does seem determined to keep its secrets. So get comfortable, let the noise of the day begin to fade, and let's start with a question that has been waiting in the dark for rather a long time. If the galaxy has had all the time in the world, why has nobody called? On a clear night, far from the glow of streetlights and windows, the sky can seem almost crowded. Stars appear in every direction, some bright and steady, others faint enough to disappear when you look directly at them. Yet even the richest night sky offers only the smallest glimpse of what is actually there. Every star visible to the unaided eye belongs to the Milky Way, but nearly all of the galaxy remains hidden from view. Dust blocks some of its light. Distance makes most stars too faint to see. Even under perfect conditions, the human eye can detect only a few thousand stars at once. The Milky Way contains roughly 100 billion stars, although estimates vary because counting every star in the galaxy is not quite as convenient as counting chairs in a quiet room. Many of those stars are accompanied by planets. Some have one or two. Others belong to systems containing several worlds, along with moons, asteroids, comets, rings, and clouds of smaller debris. Modern astronomy has shown that planets are not rare exceptions. They are ordinary products of star formation. Before the 1990s, scientists had confirmed no planets orbiting ordinary stars beyond the Sun. Today, thousands of exoplanets have been identified, and statistical studies suggest that the Milky Way contains at least tens of billions of rocky worlds. Many more planets will remain undetected because they are too small, too distant, or positioned in ways that make them difficult for our instruments to observe. Some of those worlds orbit within the habitable zones of their stars, where temperatures might allow liquid water to exist on the surface under suitable atmospheric conditions. This does not mean they are inhabited. A planet can orbit at the right distance and still be dry, frozen, airless, poisonous, or otherwise thoroughly unwelcoming. Even so, the numbers are difficult to ignore. The galaxy appears to contain an immense collection of possible environments in which life might arise. It has also existed for billions of years longer than human civilization. Many stars and planets formed before the Sun, leaving enormous amounts of time for biology, intelligence, and technology to develop elsewhere. And yet humanity has found no confirmed evidence of another technological civilization. No verified message has arrived from a distant star. No artificial spacecraft has been discovered moving through the solar system. No alien artifact has been recovered from the Moon, Mars, or any asteroid. Astronomers have not identified a megastructure surrounding another star, nor any other techno-signature that can be confidently attributed to extraterrestrial engineering. There have been strange signals, unusual stars, unexplained observations, and moments of genuine excitement. So far, however, every promising case has either received a natural explanation, been traced to human interference, or remained too uncertain to support an extraordinary conclusion. This absence is sometimes called the Great Silence. The phrase does not mean that the universe is literally silent. Space is filled with radio waves, magnetic activity, stellar explosions, colliding objects, and radiation left behind by the early universe. The silence refers specifically to the lack of convincing evidence for extraterrestrial technology. It is also important to recognize what that silence does not tell us. It does not prove that Earth is the only inhabited world. It does not prove that intelligence has never appeared elsewhere. It does not prove that no civilization is currently transmitting. It tells us only that our searches have not yet produced a confirmed detection. This distinction sits at the heart of the Fermi Paradox. Despite its name, the Fermi Paradox is not a formal contradiction in the mathematical sense. It is a tension between two ideas that both appear reasonable. The first is that the Milky Way is extremely large, extremely old, and filled with planets. The second is that we see no unmistakable evidence of anyone else. If technological civilizations are common, long-lived, and interested in spreading through space, the galaxy might be expected to contain visible signs of their existence. The fact that it does not appear to contain those signs demands an explanation. Part of the difficulty comes from the way several very different questions are often grouped together. Simple microbial life is not the same as complex life. Complex multicellular organisms are not necessarily intelligent. Intelligence does not automatically produce science or engineering. A species capable of technology may never develop radio communication or interstellar travel, and even a civilization with advanced machines may remain detectable for only a short period. Earth itself demonstrates these differences. Life has existed here for billions of years, but technological civilization appeared only very recently. For most of Earth's history, an observer on another world would have found a living planet with no radio transmitters, no artificial satellites, and no signs of industry. The silence could therefore have many explanations. Perhaps life rarely begins. Perhaps simple life is common, but complex cells are unusual. Intelligence may be a rare evolutionary accident. Technological societies may destroy themselves, become quiet, or lose interest in the outside universe. Some may deliberately hide. Others may communicate in ways we cannot detect. Interstellar expansion might be too difficult, too expensive, or simply too unappealing. Our searches may have covered far less of the galaxy than they sometimes appear to have done. Humanity may also have arrived unusually early, before most technological civilizations have had time to appear. Each possibility carries different assumptions. Some are supported by familiar biology or physics. Others depend heavily on speculation about minds and societies that may be nothing like our own. For now, the night sky offers no final answer. It simply presents an extraordinary contrast. A galaxy filled with stars, planets, chemistry, energy, and time appears to contain no obvious neighbours. Whether that silence reflects emptiness, distance, rarity, caution, bad timing, or the limitations of our search remains one of the most quietly persistent questions in modern science. The silence of the Milky Way becomes more puzzling when its age is placed beside its size. Our galaxy stretches roughly 100,000 light-years from one side to the other. Light itself, moving at the fastest speed allowed by known physics, requires about 100,000 years to cross that distance. For a human lifetime, this is almost impossible to picture. For the galaxy, however, it is a relatively brief interval. The oldest known stars in the Milky Way formed more than 13 billion years ago. Many belong to ancient populations created when the galaxy was still assembling from smaller clouds and early stellar systems. The Milky Way has therefore been producing stars, planets, and complex chemistry for nearly the entire history of the universe. The solar system is much younger. The Sun and its planets formed approximately 4.5 billion years ago, meaning that some planetary systems had already existed for billions of years before Earth appeared. Even if the first generations of stars lacked enough heavy elements to form rocky planets easily, later generations would have contained carbon, oxygen, silicon, iron, and the other ingredients needed to build solid worlds. Some planets could therefore have developed stable environments, life, intelligence, and technology long before the first animals moved through Earth's oceans. That does not mean such civilizations definitely existed. It means that time was available. Interstellar travel is slow, but it does not need to be particularly fast to become important over galactic history. A spacecraft travelling at 1% of the speed of light would still be far beyond anything humans have constructed, but it would cross the distance to a nearby star in a few centuries rather than millions of years. Crossing the entire Milky Way in one uninterrupted journey would take roughly 10 million years at that speed. A real expansion would almost certainly take longer because spacecraft would stop, systems would develop, and new expeditions would need to be prepared. Yet even a journey lasting tens or hundreds of millions of years would occupy only a small fraction of the galaxy's age. More importantly, expansion would not have to proceed as one ship travelling from one edge of the Milky Way to the other. It could unfold as a branching process. A civilization might first travel to one nearby star. After settling there, building equipment, or establishing an automated base, that new system could eventually send expeditions towards several more stars. Each of those destinations could then repeat the process. The individual journeys would remain local. Most might cover only a few light years, but the combined pattern would gradually spread outward, rather like seeds moving from one patch of ground to the next. The expansion would begin slowly. After enough settled systems existed, however, the number of possible launching points would increase. A civilization would not need to organize every expedition from its original home planet. The process could continue through independent communities, scientific organizations, machines, or descendants whose goals differed from those of the society that first began the journey. This reasoning became central to influential arguments developed by astronomer Michael Hart and physicist Frank Tipler. Michael Hart argued that if technological civilizations commonly arose and expanded between stars, one should already have reached the solar system. Frank Tipler later suggested that advanced societies could explore the galaxy using self-replicating robotic spacecraft. These hypothetical machines are often described as von Neumann probes, named after mathematician John von Neumann. Von Neumann studied the general logic of self-reproducing machines, although he did not design an interstellar probe fleet. A self-replicating spacecraft would travel to another planetary system, collect local materials, manufacture copies of itself, and send those copies onward. In principle, this could reduce the need to launch every machine from one homeworld. No fully autonomous interstellar machine of this kind currently exists. Even on Earth, building a machine capable of locating raw materials, refining them, constructing complex electronics, repairing itself, and reproducing without human support remains far beyond present engineering. The idea is nevertheless useful because it demonstrates that galactic exploration may not require biological travellers to survive every journey. Machines can potentially tolerate long periods of inactivity, harsh radiation, and very slow travel more easily than living crews. Modern computer models have examined these ideas without assuming impossibly fast spacecraft or perfectly organised expansion. Jonathan Carroll Nellenbach, Adam Frank, Jason Wright, and Caleb Scharf modelled the movement of civilizations through a changing galaxy in which stars orbit, pass near one another, and gradually create new opportunities for travel. Their simulations showed that a civilization could spread widely through the Milky Way, even when spacecraft moved slowly, and long pauses occurred between launches. The motion of stars themselves helps by bringing systems closer together over time. The results also revealed an important complication. A galaxy can become extensively settled without every star being visited. Some systems may remain isolated because of distance, timing, unsuitable conditions, or simple chance. Earth could therefore remain untouched even if settlement had occurred elsewhere. Galactic expansion also does not have to resemble a single empire covering a map. It could consist of independent settlements that lose contact with one another. Scientific probes might travel without carrying colonists. Machines could map planets and then move on. Civilizations might send libraries, artificial minds, genetic material, or dormant microorganisms rather than living populations. Some forms of expansion might be almost invisible. A small probe drifting through a planetary system would be considerably harder to detect than an enormous fleet arriving with dramatic lighting and an unnecessarily confident soundtrack. The strongest version of the argument therefore rests on a hidden assumption. At least one technological civilization must survive for long enough, retain the ability to travel, and continue choosing to spread. It must avoid permanent collapse, loss of interest, or technological retreat. Its descendants or machines must preserve some version of that outward movement across immense periods of time. If no civilization meets those conditions, the age of the galaxy may not matter, but if even one did, the Milky Way appears to have offered more than enough time for its presence to become difficult to miss. The famous question at the centre of this puzzle did not begin in an observatory, a lecture hall, or a published scientific paper. It began over lunch. In the summer of 1950, physicist Enrico Fermi was working at the Los Alamos Scientific Laboratory in New Mexico. He was already one of the most respected scientists of his generation, known for his work in nuclear physics, particle physics, and quantum theory. One day, Fermi went to lunch with three colleagues: physicist Emil Konopinski, physicist Edward Teller, and physicist Herbert York. Their conversation wandered through several subjects, as lunchtime conversations often do. Recent newspaper stories had been discussing flying saucers, following a wave of public interest in unidentified objects in the sky. A humorous cartoon had also appeared, joking that aliens might be stealing rubbish bins from the streets of New York. From there, the group began discussing whether travel between the stars was physically possible. They considered the enormous distances involved, the speed spacecraft might reach, and the length of time required for a civilization to spread from one planetary system to another. The conversation was partly serious and partly playful, but it touched on a genuine scientific issue. If technological civilizations existed elsewhere, and if some of them were much older than humanity, then at least a few might have had enough time to explore a large portion of the Milky Way. The discussion moved on to other things. Then, during lunch, Enrico Fermi suddenly asked a remarkably simple question. Where is everybody? The exact wording is not completely certain. Different people remembered the conversation in slightly different ways. Fermi may have asked where the aliens were, where the visitors were, or why there was no obvious evidence of them. Whatever the precise sentence, the meaning was clear. If the galaxy was old, if stars and planets were numerous, and if interstellar travel was possible even at modest speeds, why had no one appeared? Why were there no visitors, no spacecraft, no machines, and no unmistakable signs that another civilization had reached the solar system? It was a small question carrying an enormous amount of reasoning inside it. Fermi was famous for making quick estimates from limited information. These became known as Fermi problems. He would break a large question into smaller pieces, make sensible approximations, and arrive at an answer that was not exact, but was often surprisingly useful. He may have applied the same instinct to extraterrestrial civilization. The Milky Way was billions of years old. The distance between neighbouring stars, although immense by human standards, was not impossible to cross over long periods. A civilization capable of sending expeditions to nearby systems could gradually establish new launching points. Over enough time, the process might spread across the galaxy. If those assumptions were correct, then the absence of visitors seemed difficult to explain. The modern phrase Fermi Paradox can make it sound as though Fermi presented a complete scientific theory at lunch. He did not. He never published a formal argument called the Fermi Paradox. He did not leave behind a detailed list of assumptions or a mathematical demonstration showing that alien civilizations must exist. Much of what is known about the conversation comes from recollections collected decades later. In the 1980s, physicist Eric Jones contacted Emil Konopinski, Edward Teller, and Herbert York and asked them to describe what they remembered. Their accounts agreed on the broad shape of the discussion but differed in some details. Later, historians and scholars have therefore treated the story carefully. Fermi's original concern may have been narrower than the modern paradox. He may have been asking why Earth had not been visited if interstellar travel and expansion were common. He may not have been asking why astronomers had failed to detect radio messages, engineered stars, or distant technological activity. Those broader questions developed later. In the 1975, astronomer Michael Hart argued that the absence of extraterrestrial visitors provided strong evidence that no advanced civilization had spread through the Milky Way before humanity appeared. A few years later, physicist Frank Tipler developed a related argument involving self-replicating robotic probes. Tipler suggested that even a single technological civilization could eventually explore or influence the galaxy using machines capable of producing new copies of themselves. Radio engineer David Viewing had also published an earlier discussion of interstellar settlement and the absence of extraterrestrial visitors. Together, these arguments helped transform Fermi's lunchtime remark into the modern version of the paradox. The question was no longer only why aliens had not landed on Earth. It became a much wider problem. If advanced civilizations exist, why have we detected no confirmed radio transmissions from them? Why have astronomers found no artificial laser signals aimed across interstellar space? Why do distant stars show no verified evidence of enormous engineered structures collecting their energy? Why have telescopes detected no atmospheric chemicals that can be confidently identified as the products of alien industry? Why have we found no probes, abandoned machines, altered planets, artificial heat sources, or other clear signs of a large-scale technology? This wider absence is what is usually meant by the Great Silence. The difference matters because a civilization could exist without ever visiting Earth. It might remain within its own planetary system. It might communicate rather than travel. It might send machines instead of biological explorers. It could alter its star, produce unusual waste heat, or leave chemical traces in a planetary atmosphere. The modern search therefore looks for much more than arriving spacecraft. It looks for techno-signatures, meaning observable evidence created by technology. The uncertain history of the lunchtime conversation does not weaken the scientific question. It simply reminds us that famous ideas are often shaped gradually. Fermi provided the memorable spark. Later scientists expanded the reasoning, challenged its assumptions, and turned it into a broader investigation of life, intelligence, technology, and time. The underlying tension remains. The galaxy offers vast numbers of stars, planets, and ancient opportunities. Our observations have revealed no confirmed technological neighbours. Fermi expressed that tension as an instinctive question. The next step was to make it more systematic by asking not only where everybody was, but how many detectable civilizations should reasonably be expected to exist. The question of how many technological civilizations might exist cannot be answered simply by looking at the number of stars. A galaxy may contain an enormous number of planets, but several uncertain steps separate an ordinary world from one capable of sending a detectable signal. Astronomer Frank Drake developed a way of arranging those steps so that each could be considered separately. Before the equation came the search. In 1960, Frank Drake worked at the National Radio Astronomy Observatory in Greenbank, West Virginia. There, he used an 85-foot radio telescope to listen toward two nearby stars, Tau Ceti and Epsilon Eridani. The experiment was called Project Ozma, named after the distant land of Oz in the children's books by Lyman Frank Baum. Both stars were relatively close to Earth and broadly similar to the Sun. At the time, no planets had been discovered around either of them, but they appeared to be reasonable places to begin listening. Drake tuned the telescope near a frequency associated with neutral hydrogen, the most abundant element in the universe. The reasoning was that another technological civilization studying nature might also recognize this frequency as an obvious place to transmit. Project Ozma detected no confirmed extraterrestrial message. It did, however, demonstrate that a systematic scientific search was possible. Instead of waiting for an alien signal to arrive by chance, astronomers could choose targets, examine specific frequencies, and investigate anything unusual. The following year, in 1961, a small meeting was organised at Greenbank to discuss the search for extraterrestrial intelligence. The participants included astronomer Carl Sagan, physicist Philip Morrison, and Giuseppe Cocconi, geneticist Joshua Lederberg, chemist Melvin Calvin, radio engineer Barney Oliver, organiser Peter Pearman, and several other researchers from different scientific backgrounds. The meeting needed a clear agenda. Frank Drake therefore wrote down a sequence of factors describing the conditions that would determine how many detectable civilizations might exist in the Milky Way at any one time. That sequence became known as the Drake equation. Spoken entirely in words, it says, the number of detectable civilizations equals the rate at which suitable stars form, multiplied by the fraction with planets, multiplied by the number of potentially habitable worlds per system, multiplied by the fraction where life begins, multiplied by the fraction where intelligence develops, multiplied by the fraction producing detectable technology, multiplied by the average length of time that technology remains detectable. The first term concerns stars. New stars continue to form in the Milky Way from large clouds of gas and dust. The relevant question is how many suitable stars form during a given period. Not every star offers the same conditions. Some are extremely massive and live only briefly. Others produce intense radiation or powerful flares. Long-lived, comparatively stable stars may offer better opportunities for life to develop over billions of years. The second factor asks what fraction of those stars possess planets. When Drake created the equation, astronomers did not know whether planetary systems were common. Today, thousands of exoplanets have been confirmed, and observations suggest that planets are ordinary companions to stars. This has reduced one of the equation's original uncertainties, although it has not answered the more difficult biological questions. The third factor asks how many potentially habitable worlds exist in an average planetary system. A world may orbit within the habitable zone, where temperatures could permit liquid water, while still being unsuitable for life. Its atmosphere may be too thin, too thick, or chemically hostile. It may lack water, suffer extreme stellar radiation, or experience an unstable climate. Moons could also offer habitable environments, particularly if they contain subsurface oceans warmed by tidal forces. The next factor asks what fraction of suitable worlds actually develop life. This is one of the greatest unknowns. Life appeared on Earth relatively early in the planet's history, once stable conditions existed. That might suggest that life begins readily when chemistry and environment permit it. It could also mean that Earth was unusually fortunate. With only one confirmed living world, it is impossible to know which interpretation is correct. The following fact asks how often life develops intelligence. Evolution does not move toward a predetermined goal. For most of Earth's history, life consisted entirely of microscopic organisms. Complex multicellular organisms appeared much later, and technological intelligence emerged only once, as far as current evidence shows. Many highly successful species have survived for millions of years without developing radio telescopes, mathematics, or spacecraft. Intelligence may therefore be rare, even on planets rich with life. The next factor concerns detectable technology. An intelligent species may never build radio transmitters. It might live beneath an ocean, lack access to fire, or develop tools that leave no signal visible across interstellar distances. A technological civilization might also become difficult to detect as its systems grow more efficient. It could rely on narrow communication beams, fiber-like networks, or methods humanity has not yet imagined. The final term asks how long a civilization remains detectable. This factor is especially important because it determines how likely two technological societies are to exist at the same time. Suppose a civilization produces detectable signals for only 100 years. Even if many such societies appear over the history of the galaxy, their brief periods of visibility may rarely overlap. Now, imagine that a civilization remains detectable for 1 million years. Its signals, probes, waste heat, or engineered structures would remain observable across an enormous interval. The chance of another civilization noticing it would increase dramatically. A short, detectable lifetime can turn a busy galactic history into a quiet present. The structure of the equation also shows why multiplication matters. Imagine that 100 potentially suitable planets are considered. Suppose life begins on 1/2 of them. That leaves 50 living worlds. If complex life appears on 1/10 of those, only 5 remain. If technological intelligence develops on 1/10 of that group, the average falls below one civilization. None of the fractions in this imaginary example is impossibly small. Yet when several uncertain probabilities are multiplied together, the final result shrinks quickly. The opposite is also possible. If planets are abundant, life begins easily, intelligence appears often, and technological societies endure for millions of years, then the equation can produce a galaxy containing many detectable civilizations. The answer changes because the assumptions change. Frank Drake did not present the equation as a machine that could reliably calculate the alien population of the Milky Way. Too many of its terms were unknown in 1961, and several remain almost completely uncertain today. Its real value is organizational. The equation separates one enormous mystery into a series of clearer questions. Astronomy can investigate stars and planets. Planetary science can study atmospheres and habitable environments. Chemistry and biology can examine the origin and development of life. Evolutionary science can explore intelligence, while history, sociology, and technology may help us think about detectability and survival. The Drake equation does not prove that extraterrestrial civilizations exist. It shows precisely what humanity would need to know before making a confident estimate, and just how much of that knowledge is still missing. The Drake equation looks wonderfully tidy when written on a board. The difficulty begins when numbers must be placed inside it. Some of its terms are now understood much better than they were when Frank Drake first presented the equation in 1961. Others remain so uncertain that scientists cannot confidently say whether they should be close to 1 or almost unimaginably small. Astronomy has made the greatest progress with the early parts of the equation. For much of the 20th century, no one knew whether planets were common or whether the solar system was an unusual arrangement. That uncertainty has changed dramatically. The Kepler Space Telescope monitored the brightness of more than 100,000 stars, looking for the slight dimming produced when a planet passed in front of its star. Kepler revealed thousands of planetary candidates and showed that compact systems containing several planets are widespread. The Transiting Exoplanets Survey satellite extended this work by examining bright stars across most of the sky. Because many of its targets are relatively close to Earth, the planets it discovers are especially useful for follow-up observations with larger telescopes. The European Space Agency's Gaia mission has mapped the positions and motions of more than 1 billion stars. Gaia was not designed primarily as a planet hunter, but its extraordinarily precise measurements help astronomers understand stellar distances, masses, ages, and movements. These details improve estimates of the stars around which exoplanets are found. Ground-based observatories have added further discoveries through several methods. Some measure the tiny gravitational wobble caused by an orbiting planet. Others directly image young, massive worlds far from their stars. Together, these surveys have established that planetary systems are common. The fraction of stars possessing planets is therefore no longer a complete mystery. The more difficult question is how many of those planets provide environments where life could arise and persist. A rocky world located within the habitable zone may still be hostile. Its atmosphere might trap too much heat, as happened on Venus, or provide too little protection, as on Mars today. It might be covered by a deep global ocean, locked beneath permanent ice, stripped by stellar radiation, or subjected to extreme temperature changes. Geology also matters. Volcanic activity can release gases into an atmosphere. Weathering can remove carbon dioxide. Plate tectonics may help recycle material between a planet's surface and interior, contributing to climate stability across very long periods. Water is important for life as humanity knows it, but its location, quantity, and persistence all matter. A world may contain water only as ice, vapor, or a buried ocean beneath many kilometers of frozen crust. Magnetic fields may help protect some atmospheres from charged particles, although their importance is complex and varies between planets. The activity of the host star matters as well. Red dwarf stars live for extremely long periods, but can produce powerful flares, especially when young. A genuinely Earth-like environment is therefore more than an Earth-sized planet at roughly the right distance from a star. It is the product of atmosphere, oceans, geology, stellar behavior, chemistry, and long-term climate history. Beyond this point, the uncertainty grows rapidly. Humanity has only one confirmed example of life beginning. Life exists on Earth, but scientists do not yet know exactly how non-living chemistry became the first evolving biological system. This transition is called a biogenesis. Perhaps a biogenesis occurs readily whenever liquid water, useful chemical ingredients, and a stable energy source are present. If so, living worlds may be common. It is equally possible that the origin of life requires an extremely unlikely sequence of events. Earth may have provided countless suitable chemical environments before one finally produced a system capable of copying itself and evolving. One example cannot distinguish between these possibilities. The uncertainty surrounding intelligence is just as serious. Life appeared on Earth billions of years before any species developed radio astronomy. For most of the planet's history, life was microscopic. Even after complex organisms appeared, hundreds of millions of years passed without technology detectable across interstellar distances. Many organisms are highly successful without constructing machines. Bacteria have survived nearly every environmental change Earth has experienced. Insects occupy almost every land environment. Sharks existed long before humans and have managed perfectly well without showing much interest in radio telescopes. Evolution does not contain a rule requiring intelligence to appear. Natural selection favours traits that improve survival and reproduction in particular environments. A large brain can be useful, but it is also expensive, slow to develop, and rather demanding about breakfast. Even intelligence does not guarantee detectable technology. A species might live beneath a thick ice sheet or deep ocean, where fire and metallurgy would be difficult. It might develop sophisticated language, culture, and social organization without constructing electronic transmitters. Another civilization could build radios but use them only briefly. Human communication has already moved from powerful broadcasts toward cables, satellites, compressed digital signals, and narrow beams. A more advanced society might communicate efficiently without allowing much energy to escape into space. This means that detectability depends partly on behavior. It reflects choices, technologies, economics, values, and circumstances rather than biology alone. With optimistic assumptions, the Drake equation can produce a Milky Way containing thousands, or even millions of detectable civilizations. Planets are common, life begins easily, intelligence appears regularly, technology becomes visible, and civilizations endure for immense periods. With cautious assumptions, the expected number can fall below 1. A single extremely small biological probability, or a detectable lifetime lasting only a few centuries, can reduce the final result dramatically. Anders Sandberg, Eric Drexler, and Toby Ord examine this problem using broad probability distributions rather than selecting one confident value for each unknown term. Their analysis showed that uncertainty in the biological factors is so wide that an empty Milky Way can remain statistically plausible. This does not require life to be impossible. It means that rare events, when multiplied together, may leave humanity alone in the observable part of the galaxy. The same uncertainty also allows much more crowded possibilities. This enormous range is sometimes frustrating, but it is not a failure of science. It is an honest reflection of the available evidence. Astronomers can now count planets with growing confidence. They can study atmospheres, stars, and potentially habitable environments. But humanity still knows only one biosphere, one technological species, and one history of intelligence. Until another example is found, the numbers will continue to refuse to settle. Estimating how many civilizations might exist is only part of the problem. Even if the Milky Way contains other technological societies, astronomers still need to know what evidence those societies might leave behind. That evidence is described by the term technosignature. A technosignature is an observable sign that may have been produced by technology. It differs from a biosignature, which is a possible indication of life without necessarily implying intelligence. For example, a particular mixture of gases in a planet's atmosphere might suggest biological activity. Oxygen, methane, and other chemicals can sometimes be produced or maintained by living organisms, although natural geological processes can imitate many of these signs. A technosignature would point toward deliberate engineering or large-scale technological activity. It might be a radio transmission, an artificial light source, an industrial chemical, a spacecraft, or an unusual pattern of energy use. Radio signals remain among the most familiar possibilities. Natural objects produce enormous amounts of radio emission, but those signals usually spread across a range of frequencies. A narrowband transmission concentrated within a very small frequency range can therefore attract attention, because it resembles the kind of signal produced by technology. A civilization might transmit a powerful radio beacon deliberately, perhaps repeating a simple pattern or directing it toward nearby stars. Microwave communication could serve a similar purpose, particularly because some microwave frequencies can travel efficiently through interstellar gas and dust. Optical searchers look for brief flashes of laser light. A sufficiently powerful laser could momentarily outshine a star within a very narrow wavelength. Repeated pulses arranged in a recognizable pattern would be especially interesting. Directed energy systems might also produce detectable effects without being intended as messages. Powerful lasers could be used to push spacecraft, transmit energy between planets, move small objects, or defend a planetary system from asteroids. Not every techno-signature would involve communication. Astronomers may eventually detect artificial chemicals in an exoplanet's atmosphere. Industrial pollutants with no convincing natural source could indicate manufacturing, energy production, or some other form of large-scale engineering. Artificial illumination is another possibility. A planet's night side might glow more brightly than natural reflected light or atmospheric activity could explain. Detecting city lights across interstellar distances would be extremely difficult, but a civilization illuminating a large part of its planet might leave a measurable signature. The largest technologies could influence entire planetary systems. In 1960, physicist Freeman Dyson proposed searching for advanced civilizations by examining how they use the energy of their stars. The idea later became associated with the term Dyson sphere. A Dyson sphere is often imagined as a solid shell surrounding a star. That was not the most realistic version of Dyson's proposal. A rigid shell would face enormous structural and gravitational difficulties. Dyson instead considered a distributed collection of energy-gathering structures orbiting a star. This arrangement is now commonly called a Dyson swarm. A sufficiently large swarm of satellites, habitats, or collectors could intercept a substantial fraction of the star's light. From a great distance, the star might appear unusually dim in visible light while producing excess infrared radiation. This follows from the conservation of energy. Energy does not simply disappear after it has been used. A civilization powering machines, computers, habitats, or industries would eventually release much of that energy as heat. If a society captured an enormous amount of starlight, some of that energy should emerge again as lower temperature infrared radiation. Astronomers can therefore search for objects whose visible and infrared output looks unusual. Natural dust can also absorb starlight and produce infrared emission, so an unusual heat signature would not automatically prove the existence of technology. It would instead become a candidate requiring careful investigation. Physical artifacts might be found much closer to home. Interstellar probes could pass through planetary systems or remain in stable orbits for long periods. Abandoned machines might survive on airless moons, asteroids, or distant objects where erosion is slow. A civilization could alter asteroids for mining, construct artificial satellites around planets, move smaller worlds, or change the output of a star. Some modifications might remain visible long after the civilization responsible had vanished. The possible scale of such activity was organized by astronomer Nikolai Kardashev into a rough classification based on energy use. A civilization at the first level would use energy on the scale available across its home planet. A civilization at the second level would control a substantial fraction of the energy produced by its star. A civilization at the third level would use energy across much of an entire galaxy. Human civilization has not yet reached the first level under the original definition. The Kardashev scale is useful for imagining the possible visibility of advanced technology. A society using the energy of a galaxy should be considerably easier to notice than one operating a few efficient computers beneath the surface of a quiet moon. It should not, however, be treated as an inevitable path. Technological advancement does not have to mean continuously using more power. A civilization may become smaller, more efficient, or more interested in computation than construction. It might deliberately limit growth or concentrate its activity in places that are difficult to observe. There is also an important difference between a deliberate beacon and accidental leakage. A powerful beacon aimed directly at Earth could potentially be detected from a great distance. Ordinary radio and television broadcasts are much weaker and spread outward in many directions. As that energy travels, it is distributed across an expanding area. By the time it reaches another star, the signal may be too faint to separate from natural background noise. Humanity's radio leakage is therefore not necessarily announcing our presence across the entire Milky Way with quite the enthusiasm sometimes imagined. Every search for extraterrestrial technology contains assumptions. Astronomers must guess which stars to examine, which frequencies to monitor, how long to listen, what level of power to expect, and whether another civilization wants to be detected. They must also imagine what alien engineers might build. how they might communicate, and which traces their activities would leave behind. The quiet sky may reflect an absence of technology. It may also reflect the narrower fact that humanity has been searching for unfamiliar civilizations using instruments designed around familiar human ideas. The silence of the galaxy can be approached in many ways, but one of the most influential ideas begins with a simple observation. Somewhere between lifeless matter and a civilization capable of spreading between the stars, at least one step may be extraordinarily difficult. This idea is known as the Great Filter. Economist Robin Hanson developed the modern formulation in 1998. His argument was not that scientists had discovered a single hidden force preventing civilizations from advancing. Instead, he asked what the apparent emptiness of the galaxy might suggest about the long sequence of events required to produce a widespread technological society. That sequence begins before life exists at all. A suitable star must form and remain stable for long enough. Around it, a planet or moon must develop conditions that allow complex chemistry to persist. Useful elements must be available. Temperatures, energy sources, and liquid solvents must remain within workable ranges. Then non-living chemistry must somehow produce a system capable of copying itself. This transition from chemistry to self-replicating biology is the origin of life, often described by the term abiogenesis. Scientists understand many of the chemical ingredients involved, but no one yet knows how probable the complete transition is. Once life begins, simple cells must survive, reproduce, and evolve. At some point, more complex cells may appear. On Earth, eukaryotic cells developed internal structures and eventually allowed much larger and more complicated organisms to evolve. Multicellular life must then emerge and persist. Nervous systems may develop. Intelligence may arise. A species must become capable of cumulative culture, language, tool-making, and the long-term preservation of knowledge. Technology must advance far enough to produce astronomy, industry, communication systems, and perhaps spacecraft. After that, a civilization must survive its own growing power. It must avoid permanent collapse or extinction, and remain stable long enough to expand beyond its original world. Finally, it must actually choose to spread or create detectable activity across interstellar distances. Every one of these stages may appear possible when considered alone. The Great Filter asks whether one or more of them is so improbable that almost no world completes the entire sequence. A useful way to imagine this is as a long corridor filled with locked doors. A vast number of planets may enter through the first doorway simply by forming around suitable stars. Fewer may pass through the door, leading to stable oceans or useful chemistry. A smaller group may reach self-replicating life. Fewer still may produce complex cells, multicellular organisms, intelligence, and technology. Even if each door is only moderately difficult to open, the combined journey can become extremely unlikely. Suppose 1 world in 10 passes each stage. After 1 door, many worlds remain. After 2, the number is smaller. After several doors, only a tiny fraction of the original group reaches the end. The filter therefore does not need to be a single dramatic event. There may be no universal catastrophe that suddenly removes every civilization at the same point. Instead, the Great Filter could be distributed across many difficult transitions. The origin of life may be rare. Complex cells may be rarer still. Technological intelligence may emerge only occasionally. Long-term survival may eliminate most of the civilizations that reach that stage. Several unlikely events multiplied together could produce a nearly empty galaxy. The location of the filter is what makes the idea so important. If the hardest steps lie behind humanity, then our existence suggests that Earth has already passed through something exceptionally unusual. Perhaps abiogenesis almost never happens. Perhaps the formation of complex cells was a rare evolutionary event. Perhaps intelligence capable of science and technology is extraordinarily uncommon. Under this interpretation, the silence of the galaxy is partly reassuring. Humanity has already crossed the most difficult barriers, although survival is never guaranteed. There is another possibility. The greatest filter may lie ahead. Perhaps life begins often, and intelligence appears on many worlds. Technological civilizations may rise repeatedly, only to disappear before they become stable, long-lived, and capable of spreading through the galaxy. They may destroy themselves through warfare, environmental collapse, uncontrolled technology, or some danger humanity has not yet encountered. They might also fail without becoming extinct. A civilization could lose its technological capacity, turn inward, abandon expansion, or remain confined to one planetary system until natural events eventually remove it. This possibility is more unsettling because humanity has already reached the stage where powerful technology exists, but long-term survival is uncertain. Robin Hanson's reasoning begins with the apparent emptiness around us. If suitable planets are common, life begins easily, intelligence evolves regularly, technological societies survive, and interstellar expansion is practical, then the Milky Way should contain visible traces of those societies. There should be probes, settlements, artificial signals, altered planets, unusual energy use, or some other clear technosignature. If all the steps are easy, the silence becomes difficult to explain. The Great Filter offers one answer by suggesting that the full path is not easy at all. It is important, however, not to treat the filter as something directly observed. Astronomers have not detected a physical barrier preventing life from advancing. There is no invisible wall positioned between radio communication and interstellar travel, waiting patiently to ruin everyone's plans. The Great Filter is an inference built from several uncertain assumptions. It assumes that technological civilizations would often become detectable. It assumes that at least some would expand. It assumes that our searchers are capable of finding the signs they would produce. If those assumptions are wrong, the galaxy could contain civilizations without requiring any overwhelmingly difficult filter. Humanity also has only one known example of life, intelligence, and technology. Earth cannot reveal which transitions are common and which are rare because every stage in our own history happened at least once. The Great Filter therefore remains a framework rather than a confirmed solution. Its central question is still powerful. Have humans already passed through the least probable stages in the history of life? Or have we simply reached the point where the most difficult door is waiting ahead? If the Great Filter lies mostly behind humanity, then our existence may be the result of several events that almost never happen. This is the more optimistic interpretation of the Great Filter. It suggests that the most difficult barriers have already been crossed, hidden deep within the biological history of Earth. The first possible barrier is the origin of life itself. Abiogenesis is the process by which non-living chemistry gave rise to the first systems capable of maintaining themselves, reproducing, and evolving. Scientists have identified many of the necessary ingredients, including organic molecules, sources of energy, liquid water, and chemical environments where complex reactions can occur. What remains unknown is how these ingredients became organized into the first genuine living system. Early Earth contained oceans, volcanic environments, mineral surfaces, hydrothermal systems, and a rich mixture of simple chemicals. Under some conditions, organic molecules can form naturally. Laboratory experiments have also shown that amino acids, nucleic acid components, and membrane-like structures can arise without biology. Yet none of this reveals how often the complete transition occurs. Life appears relatively early in Earth's geological history. The planet formed about 4.5 billion years ago, and evidence suggests that life existed at least 3.5 billion years ago, perhaps earlier. This can be interpreted in two very different ways. Perhaps life begins readily once a planet becomes stable enough. If suitable chemistry and liquid water are present, biology may follow fairly quickly. But there is another explanation. Observers can only appear on a planet where life began early enough to leave time for intelligence to evolve. Our own existence therefore guarantees that we find ourselves on a world where abiogenesis happened reasonably early, even if the event is usually extremely rare. One successful example cannot show whether life appears easily or whether Earth won an astonishing chemical lottery. Another possible filter lies in the development of complex cells. For much of Earth's history, every organism was microscopic. The planet was alive, but life consisted mainly of relatively simple cells known as prokaryotes. Complex cells, called eukaryotic cells, appeared much later. These cells contain internal structures, including a nucleus and energy-producing mitochondria. The origin of mitochondria is explained by endosymbiosis. A free-living bacterium entered another cell and, instead of being digested, formed a lasting partnership with it. Over immense periods, the bacterium became an essential internal component of the larger cell. Biologist Lynn Marzulis played a central role in developing and defending the modern endosymbiotic theory. The idea was initially resisted but is now strongly supported by genetic and structural evidence. Mitochondria retain their own small amount of genetic material and possess features linking them to ancient bacteria. This merger may have transformed what life could become. Mitochondria provided complex cells with highly effective energy production, helping support larger genomes, specialized internal structures, and eventually complex multicellular organisms. If this kind of biological union is extremely rare, many inhabited planets might remain microbial for their entire histories. The next steps are no less uncertain. Multicellularity must develop in a form capable of producing complex bodies. Cells must cooperate, specialize, and regulate their growth. Nervous systems may need to emerge, followed by advanced senses, memory, learning, and flexible behavior. Intelligence alone is not enough. A species must develop language capable of transferring detailed knowledge. It needs cumulative culture, so discoveries can be preserved and improved rather than repeatedly lost. Abstract reasoning must become useful. Precision tool-making must be possible. Energy sources must be controlled. Materials must be shaped, and observations must eventually be turned into organized science. On Earth, these developments did not arrive as one sudden package. They accumulated through a long sequence of biological and cultural changes. Many intelligent animals never developed scientific technology. Dolphins display complex communication and social behavior, yet their ocean environment makes controlled fire and metallurgy nearly impossible. Crows can solve difficult problems and manufacture simple tools, but they do not build observatories. Octopuses are remarkably capable, although their short lives and largely solitary behavior may limit the accumulation of knowledge across generations. Human technology depended not only on intelligence, but also on hands, language, cooperation, long childhoods, accessible materials, and an environment where fire could be controlled. Astrophysicist Brandon Carter developed a related idea known as the hard step model. The model proposes that intelligent observers may require several highly improbable evolutionary transitions. Each hard step takes a very long and unpredictable amount of time, and all of them must occur before a planet's habitable period ends. Earth will not remain suitable for complex surface life forever. As the sun gradually becomes brighter, long-term climate conditions will change. If intelligence appeared relatively late within Earth's total habitable lifetime, that may suggest that several difficult steps were required. The timing alone does not identify those steps. They might include abiogenesis, complex cells, multicellularity, advanced intelligence, or some transition scientists have not recognized. Discovering independent extraterrestrial life would greatly affect this reasoning. Life found on Mars could show that biology began twice within one planetary system, provided it did not share an origin with Earth life through material exchange by asteroid impacts. The ocean beneath the ice of Europa, a moon of Jupiter, may contain environments where life could exist. Enceladus, a moon of Saturn, releases plumes containing water, salts, organic compounds, and other material from its hidden ocean. Evidence of life on either moon would be extraordinary. Evidence that it arose independently would be even more important. A biosignature in the atmosphere of an exoplanet could also suggest that life is not unique to Earth, although such evidence would require careful confirmation because non-biological processes can imitate many possible biosignatures. If simple life is discovered almost everywhere scientists look, abiogenesis would begin to seem less likely as the main filter. If complex multicellular life is also common, another possible barrier would weaken. Some people therefore describe the discovery of widespread extraterrestrial life as potentially bad news. The reasoning is that each common early step pushes the great filter further toward the future. That conclusion is not automatic. Its meaning would depend on what kind of life was found, whether it had an independent origin, how common it appeared to be, and which assumptions were already considered plausible. A single microbe on Mars would not prove that intelligence is common. A planet covered in forests would not prove that technological civilization is inevitable. The quiet galaxy may still reflect an extraordinarily difficult path from chemistry to complex cells, from animals to intelligence, or from intelligence to cumulative scientific culture. If that is true, humanity may already have passed through the narrower section of the journey. It would be reassuring in one sense, but also deeply humbling. The silence would suggest that a universe filled with planets can remain almost entirely without minds capable of noticing them. The more unsettling version of the Great Filter places its most difficult barrier not in the distant biological past, but somewhere ahead of technological civilization. Under this possibility, life may begin on many suitable worlds. Complex organisms may appear more than once. Intelligence might even evolve regularly. The problem would arrive later. A species may develop science, industry, and powerful technology, yet fail to remain stable for long enough to spread beyond its home system. Civilizations could appear repeatedly throughout galactic history and disappear before leaving durable evidence behind. This possibility connects directly to the final term in the Drake equation, the length of time a civilization remains detectable. A technological society visible for only a few centuries occupies an extremely narrow window in cosmic time. Even if thousands of civilizations have existed across the history of the Milky Way, very few may overlap. One could rise around a distant star, transmit for several hundred years, and vanish millions of years before humanity learned to build a radio telescope. Another might not appear until long after Earth is gone. A galaxy can therefore produce intelligence many times while containing almost no detectable civilizations at any particular moment. The causes of short technological lifetimes could vary. Nuclear warfare is one possible danger. A civilization capable of understanding atomic physics may eventually gain the ability to destroy cities, damage ecosystems, and disrupt the systems on which its population depends. That does not mean nuclear technology inevitably causes extinction. Humanity has possessed nuclear weapons for decades without using them in a full global war. The risk lies in accidents, miscalculation, political instability, escalation, and the increasing destructive power available to a relatively small number of decisions. Biotechnology may create another period of danger. The same knowledge used to develop medicines, vaccines, and disease treatments could also make it possible to alter dangerous organisms. An engineered pathogen might spread more effectively than a naturally occurring disease or target particular species and crops. Again, capability does not guarantee catastrophe. Strong laboratory standards, monitoring, public health systems, and international cooperation can reduce the danger. The concern is that destructive abilities may sometimes develop faster than reliable safeguards. Ecological damage could act more slowly. A technological civilization depends on functioning environments, stable food production, clean water, manageable temperatures, and access to essential materials. If industrial growth damages these systems faster than institutions can respond, the result may be conflict, migration, instability, and decline. Resource problems are rarely simple matters of a planet suddenly running out of everything. Shortages become dangerous when they combine with inequality, weak governance, political distrust, and competition between groups. Artificial intelligence is often included among possible future risks. Advanced systems could support scientific research, medicine, education, engineering, and environmental management. Poorly designed or poorly governed systems might also behave in unexpected ways, concentrate power, destabilize societies, or pursue objectives that do not match human needs. There is no scientific evidence that artificial intelligence must destroy a technological civilization. The risk depends on what is built, how it is controlled, who controls it, and whether institutions develop alongside the technology. These possibilities do not all lead to total extinction. A civilization might collapse while some individuals survive. Large populations and complex institutions could disappear without the species itself vanishing. Technology could regress, knowledge might be lost, infrastructure could decay, and future societies might never rebuild the systems needed for astronomy or interstellar travel. A civilization could also remain healthy while becoming quieter. It might deliberately reduce industrial activity, stop broadcasting, limit growth, or decide that expansion beyond its own planetary system is unnecessary. From a distant telescope, extinction, collapse, regression, and voluntary silence could all produce a similar result. The techno-signature fades. Technology is therefore neither purely a threat nor purely a protection. Nuclear physics creates weapons, but it also provides energy and helps scientists understand stars. Biotechnology can produce pathogens, but it can also detect outbreaks and develop treatments. Advanced astronomy allows a civilization to identify asteroids before they strike. Spacecraft can test methods of changing an asteroid's path. Satellites can monitor climate, weather, forests, oceans, fires, and crop health across an entire planet. Settlements beyond one world could eventually reduce the danger of a single planetary disaster, although creating truly independent populations would be extraordinarily difficult. Natural threats remain as well. Large asteroid impacts have caused major disruptions in Earth's history. A sufficiently large impact could devastate global ecosystems, although events capable of sterilizing an entire planet are far rarer. Supervolcanic eruptions could cool the climate, damage agriculture, and cause widespread hardship. Nearby supernovae and gamma-ray bursts could expose a planet to harmful radiation, though such events are uncommon at dangerous distances. Over much longer timescales, the increasing brightness of a star may eventually make a planet uninhabitable. Earth itself cannot remain suitable forever as the sun gradually changes. Most natural disasters would not remove every form of life. Many would be far more likely to destroy civilization than to sterilize a whole world. A particularly vulnerable period may begin when a species gains planet-altering power, before developing the institutions needed to manage that power reliably. Scientific capability can grow rapidly. Political systems, laws, ethical standards, and international agreements often change more slowly. A young technological civilization may therefore possess extraordinary tools while still carrying instincts shaped for small groups, short-term problems, and local competition. Humanity may currently be living within that imbalance, but our continued existence tells us almost nothing about how often civilizations survive it. We are one technological species, observing ourselves near the beginning of our technological history. We do not know whether this stage usually lasts for centuries, millions of years, or only long enough for a civilization to notice the danger. The great filter ahead is not a prediction that destruction is inevitable, it is a warning drawn from uncertainty. The silence of the galaxy may suggest that survival requires more than intelligence. It may require restraint, cooperation, resilience, careful institutions, and the ability to plan beyond a single lifetime. Seen in that way, the quiet sky does not demand fatalism. It offers a reason to become the kind of civilization capable of remaining present long enough to be heard. One possible explanation for the silence of the galaxy is that life may not be especially rare, but complex life may be. This idea is known as the rare Earth hypothesis. It is closely associated with geologist Peter Ward and astronomer Donald Brownlee, who argued that simple microbial life could be widespread, while complex animal-like organisms require an unusually fortunate combination of planetary and astronomical conditions. The hypothesis does not claim that Earth is the only living world. Instead, it suggests that the path from a habitable planet to a world containing large, complex, intelligent organisms may be much narrower than it first appears. A suitable star is one important part of that path. The star must remain stable for long enough to give life time to develop. Very massive stars burn through their fuel quickly and may survive for only millions of years. That is enough time for planets to form, but perhaps not enough for complex biology to evolve. Smaller stars live much longer, although some produce intense flares and energetic radiation, particularly when they're young. A star like the Sun offers a relatively long and stable period, during which planetary environments can change gradually. The planet must also orbit at a suitable distance. A world too close to its star may become extremely hot. Its oceans could evaporate, and a runaway greenhouse effect could produce conditions resembling those on Venus. A planet too far away may remain frozen. Liquid water might survive below the surface, but sunlight-driven ecosystems would face different limitations. The habitable zone describes the range of distances where surface liquid water could exist under suitable atmospheric conditions. It is a useful starting point, but it is not a guarantee of habitability. The atmosphere matters just as much as the orbit. It must retain enough heat to prevent permanent freezing without trapping so much that the surface becomes dangerously hot. It may also need to shield life from harmful radiation, transport heat around the planet, and maintain pressures that allow water to remain liquid. Long-term climate stability could depend on geology. Earth's plate tectonics continually moves and recycles sections of the crust. Volcanoes release carbon dioxide from the interior, while rain and chemical weathering gradually remove carbon dioxide from the atmosphere. Some of that carbon becomes locked into rocks and sediments. Plate tectonics eventually carries this material into the planet's interior, where volcanic activity can return it to the atmosphere. This process forms part of the long-term carbon cycle. Because carbon dioxide is an important greenhouse gas, the carbon cycle may help regulate Earth's temperature across hundreds of millions of years. A warmer climate can increase weathering, which removes more carbon dioxide and produces a cooling effect. A cooler climate can reduce weathering, allowing volcanic carbon dioxide to accumulate. The system is not perfect, and Earth has experienced severe climate changes, including periods of extensive global ice. Even so, geological recycling may have helped prevent the planet from remaining permanently frozen or overheated. Scientists do not yet know whether plate tectonics is essential for complex life. Another planet might regulate its climate through different geological processes. It might possess moving crust, intermittent tectonic activity, or an entirely unfamiliar relationship between its surface and interior. Earth's moon is another frequently discussed factor. The moon is unusually large compared with Earth. Its gravity produces strong tides, which may have influenced coastal habitats and early biological environments. The moon also affects Earth's rotation and helps limit changes in the tilt of its axis. A relatively stable axial tilt can support more predictable long-term seasons. Without the moon, Earth's tilt might vary more strongly over geological time, creating greater climate changes. However, computer models do not all agree on how severe those variations would be, and scientists cannot yet say that a large moon is required for complex life. The moon may have been helpful without being essential. Jupiter is often described as Earth's protective shield. Its immense gravity can capture comets, alter their orbits, or eject them from the solar system. This has encouraged the idea that Jupiter reduced the number of dangerous impacts reaching Earth. The true picture is more complicated. Jupiter can remove some objects, but its gravity can also redirect asteroids and comets toward the inner solar system. Depending on the original orbit of an object, Jupiter may reduce or increase the danger. It is therefore not simply a large and considerate guardian standing at the edge of the neighbourhood. Its gravitational influence is powerful, but not always protective. The rare Earth hypothesis includes many additional conditions. A planet must have enough mass to retain an atmosphere, but excessive mass could produce crushing pressures or a deep envelope of hydrogen and helium. A magnetic field may help protect an atmosphere from charged particles released by the host star, although planets without strong global magnetic fields can sometimes retain substantial atmospheres. The balance between oceans and continents may matter. Oceans regulate temperature and provide stable environments, while exposed land supports weathering and creates varied ecological settings. Too much water could bury the rocky crust beneath a deep global ocean. Too little could limit biological activity. Complex animal life on Earth also depends heavily on atmospheric oxygen. For much of the planet's history, oxygen levels were far lower than they are today. Large active organisms became possible only after photosynthetic life transformed the atmosphere and oceans. The wider galactic environment may influence habitability as well. A planetary system located too close to the galactic centre might experience more nearby supernovae, stronger radiation, and greater gravitational disturbance. A system much farther out may contain fewer heavy elements from which rocky planets can form. This has led to the idea of a galactic habitable zone, although its exact boundaries remain uncertain. Orbital stability, nearby stars, asteroid populations, the chemistry of the planet, the behaviour of the host star, and the timing of major evolutionary events may all contribute. When these factors are combined, Earth can appear like the result of an exceptionally fortunate arrangement. There is, however, an important danger in reasoning backward from our own planet. Earth is the only inhabited world we know, so every feature of Earth may seem important simply because it is present here. We have a large moon, plate tectonics, continents, oceans, a magnetic field, and Jupiter nearby. It is tempting to declare all of them essential, but this would be like examining one successful garden and concluding that every garden in the universe must contain exactly the same soil, rainfall, insects, and number of slightly judgmental pigeons. Complex life elsewhere may follow a different path. It could develop on a world with no large moon, beneath a global ocean, around a smaller star, or with a different atmospheric chemistry. Its biology might use unfamiliar molecules, or thrive under pressures and temperatures that would be hostile to humans. The rare Earth hypothesis is therefore not proof that Earth's arrangement is uniquely capable of supporting complex life. Its value lies in challenging the easy assumption that a planet located in the habitable zone will naturally develop animals, intelligence, and technology. Microbial life may require only chemistry, energy, and time. Complex life may demand a much longer list of conditions, maintained in the right balance for billions of years. If that list is unusually difficult to complete, then the galaxy may contain many living worlds while remaining almost entirely silent. The silence of the galaxy may not mean that technological life is almost impossible. It may simply mean that humanity has arrived unusually early. The universe is approximately 13.8 billion years old. That sounds ancient, and by human standards it certainly is. Yet the full lifetime of the universe may stretch far beyond its present age. Some stars will continue shining for trillions of years. The smallest and longest-lived stars use their nuclear fuel extremely slowly. While a star like the Sun remains stable for roughly 10 billion years, a very low-mass red dwarf may continue producing light for thousands of times longer. From this wider perspective, the universe may still be near the beginning of its life-producing era. The first stars were not accompanied by immediately habitable planets. Soon after the Big Bang, the universe contained mostly hydrogen and helium, along with very small quantities of a few lighter elements. Carbon, oxygen, silicon, iron, and many other elements needed for rocky planets and complex chemistry did not yet exist in useful amounts. Those elements were manufactured inside stars. Nuclear fusion in stellar cores gradually built heavier atomic nuclei. When massive stars reached the ends of their lives, they returned newly formed material to space through stellar winds and supernova explosions. Later generations of stars formed from gas enriched by the remains of earlier ones. Their surrounding disks contained more of the solid material required to produce rocky planets, moons, oceans, atmospheres, and living chemistry. The universe therefore needed time before worlds resembling Earth could become common. Biological opportunity emerged gradually. Galaxies had to assemble. Stars had to form, live, and die. Heavy elements had to spread through interstellar space. New stars then had to gather that enriched material into planetary systems. The oldest rocky planets may have appeared billions of years before Earth, but they were not present at the beginning of cosmic history. This raises an important possibility. Perhaps humanity is early not compared with every planet that has ever existed, but compared with the enormous number of habitable worlds that may appear in the distant future. Astrophysicists Abraham Loeb, Rafael Batista, and David Sloan examined this question by estimating when life is most likely to arise over the full lifetimes of different kinds of stars. Their research suggested that if planets around low-mass red dwarf stars can remain habitable, then the greatest opportunity for life may lie trillions of years ahead. Red dwarfs are the most common stars in the Milky Way. They are smaller, cooler, and dimmer than the Sun. Because they consume their fuel so slowly, they can remain active for extraordinarily long periods. A planet orbiting one of these stars could, in principle, have far more time for life to begin and evolve than Earth has had around the Sun. This gives red dwarf systems an obvious advantage. Time is one of the most important ingredients in the development of complex life. Earth required billions of years to move from its earliest organisms to animals, intelligence, and technological civilization. A stable planet around a red dwarf might possess not merely billions of years, but hundreds of billions or even trillions. However, long stellar life does not automatically produce good living conditions. A red dwarf is faint, so a planet must orbit close to the star to receive enough warmth for liquid water. At such a short distance, the planet may become tidally locked. One side may continually face the star while the other remains in darkness. Tidal locking is not necessarily fatal to habitability. A sufficiently thick atmosphere or deep ocean might transport heat between the day side and the night side, preventing either region from becoming completely extreme. The greater concern may be stellar activity. Young red dwarfs can produce powerful flares and bursts of high-energy radiation. They may also release streams of charged particles capable of affecting or eroding nearby planetary atmospheres. Because the habitable zone lies so close to the star, planets receive this activity at much shorter distances than Earth receives solar storms from the Sun. Red dwarfs can remain highly active for long periods. A planet may therefore spend hundreds of millions or even billions of years being exposed to intense radiation before its star becomes calmer. An atmosphere might survive if it is sufficiently thick, regularly replenished by volcanic activity, or protected by other planetary processes. Water could also remain beneath the surface, even if conditions above become harsh. At present, scientists do not know whether red dwarf systems are usually hostile, occasionally habitable, or some of the best long-term homes for life in the universe. That uncertainty is crucial. If planets around red dwarfs commonly support life, then most biological history may still lie in the future. Humanity would belong to one of the early generations of technological species, appearing before the universe reaches its most productive era. The galaxy might be quiet because very few civilizations have yet had time to arrive. This possibility weakens the Fermi Paradox, but it does not remove it entirely. Even if humanity is early compared with the trillions of years ahead, many stars and planets in the Milky Way are already much older than the solar system. Some potentially suitable worlds could have formed 1 billion, 2 billion, or several billion years before Earth. That would provide more than enough time for life to begin, evolve intelligence, develop technology, and leave detectable traces, assuming those steps are reasonably common. The early arrival idea therefore cannot explain every part of the silence by itself. It may help explain why the galaxy is not crowded with ancient civilizations, but it still leaves open the question of why none of the older planetary systems appear to have produced one that became visible. The answer may involve several factors working together. Humanity could be relatively early, while life is also uncommon. Red dwarf planets might be difficult places for biology. Intelligence may require long and improbable evolutionary transitions. Civilizations may remain detectable for only brief periods. Cosmic history does not need to provide one single explanation. The quiet sky may reflect timing as well as rarity. The universe is old enough to have produced stars, planets, life and intelligence, but it may still be young compared with everything that remains possible. In that case, the Milky Way is not an abandoned place after the story has ended. It is more like a vast theatre before most of the audience has arrived, with only a few early visitors sitting quietly in the darkness and wondering why the room seems so empty. The Fermi Paradox often assumes that a successful civilization will eventually spread beyond its home system. That assumption may be reasonable for some societies, but it does not have to be true for all of them. A civilization could become technologically advanced, survive for millions of years, and still decide that crossing the galaxy is neither necessary nor desirable. Interstellar travel would remain difficult even for a society far beyond humanity. The distance between neighbouring stars is measured in light years. A spacecraft moving at a small fraction of the speed of light could complete the journey, but the voyage might still last for decades, centuries, or longer. During that time, the craft would need to survive radiation, impacts from dust, mechanical failure, and the gradual degradation of its materials. Every important system would require redundancy, repair, or some method of replacing damaged components. A crewed mission would face additional problems. Living travellers need food, energy, protection, stable habitats, and environments capable of functioning across generations. Human bodies are poorly suited to long periods in low gravity and intense radiation, although another species might be more adaptable. The destination would also be uncertain. A planet that appears promising from several light years away may turn out to have an unstable climate, an unbreathable atmosphere, dangerous chemistry, or no accessible resources. Communication creates another difficulty. A message sent back to the home system would take years to arrive. Any reply would require the same journey in the opposite direction. A settlement only 20 light years away would wait at least 40 years for a complete exchange. Its decisions would quickly become local decisions, made without immediate guidance from the civilization that launched it. Interstellar expansion may therefore produce separation rather than unity. This does not make expansion impossible. It may simply make it less attractive than it appears from the comfortable side of a telescope. Jacob Huck Misra and Seth Baum developed an explanation sometimes called the sustainability solution. Their argument challenges the assumption that technological civilizations must continue growing exponentially. Exponential growth begins gently but accelerates rapidly. If a population, industry, or settlement network keeps multiplying at a fixed rate, it eventually demands enormous amounts of energy, material, and space. No physical system can expand exponentially forever. A long-lived civilization may therefore learn to stabilize its population and resource use rather than continually increasing both. Its survival could depend on becoming more efficient, more careful, and less expansionist. Under this view, a civilization that lasts for millions of years may not resemble an empire constantly occupying new territory. It could remain within one planetary system while developing sophisticated habitats, recycling materials, and managing energy with extreme precision. Ecological preservation might become more important than growth. A society with a deep understanding of planetary systems may treat living worlds as rare environments to be protected rather than resources waiting to be used. Local knowledge may also become valuable. A civilization that has spent thousands of years studying its own planet, star, moons, and neighbouring objects may prefer that familiar environment to the uncertainty of distant systems. Expansion is often imagined as progress, because human history has frequently connected growth with wealth, security, and influence. An older society might define progress differently. It may value stability, cultural continuity, scientific understanding, or quality of experience rather than the number of worlds it occupies. Virtual environments could reduce the pressure to expand physically. If minds can experience rich artificial worlds, the available space inside computation might matter more than the amount of land on distant planets. Compact computing systems could contain enormous libraries, simulated environments, and perhaps conscious digital beings while occupying only a small physical region. A civilization might therefore become more inwardly complex while becoming less visible from outside. Post-biological societies are sometimes discussed in this context. A species could create machine intelligence or develop methods of preserving minds in artificial forms. Such entities would not necessarily need Earth-like planets, breathable atmospheres, or warm biological habitats. They might prefer cold regions because computing systems can release waste heat more efficiently at low temperatures. A machine civilization could settle distant objects, shadowed moons, or isolated regions far from bright stars. It might use energy carefully and communicate through tightly directed signals. This would make it very different from the bright, expanding galactic empire often imagined in science fiction. It is important not to treat post-biological life as an established destination for technological species. Humanity does not know whether artificial consciousness or mind uploading is physically achievable. The idea simply illustrates how advanced civilization might become quieter rather than louder. Even if most members of a society reject expansion, however, that may not be enough to prevent it completely. One independent group could leave. A religious movement, scientific organization, political faction, commercial project, machine system, or adventurous community might decide to travel despite the preferences of the wider population. Once a distant settlement becomes independent, its descendants may make different choices. A civilization does not need a single coordinated plan lasting millions of years. It may spread through repeated acts by small groups that value exploration, isolation, survival, or simple curiosity. This makes total restraint difficult. A society might oppose expansion for 10,000 years, only for one later generation to change its mind. A self-directed machine could continue travelling after the culture that created it had disappeared. The galaxy may therefore contain both expansionist and non-expansionist societies, along with every uncertain arrangement between them. Modern simulations sometimes describe a related possibility known as the aurora effect. Jonathan Carroll Nellenbach, Adam Frank, Jason Wright, and Caleb Scharf modelled settlement in a galaxy where stars move, spacecraft travel slowly, and long pauses can occur between expeditions. Their results showed that expansion can become widespread without reaching every system. Some stars are visited repeatedly, others remain untouched because they are poorly positioned, unattractive, or simply missed by the moving front of settlement. The motion of stars creates changing opportunities. Two systems that are far apart today may pass closer together in the future. A settlement may expand during one period and become isolated during another. This produces a galaxy that is neither completely empty nor completely occupied. Earth could exist within one of the unvisited regions. A civilization may also expand only briefly. It might establish a few settlements, then stop. Those settlements could become independent, lose contact, or develop cultures that no longer resemble the original society. Some branches might collapse. Others could abandon technology, turn inward, or disappear. Their machines may continue operating after their creators are gone, or their descendants may become so different that speaking of one civilization no longer makes much sense. An expansion that began as a unified project could gradually become a scattered collection of unrelated societies. From Earth, such a galaxy might still appear quiet. The most active regions could be distant. The nearest settlements might use little energy, communicate rarely, or have no interest in crossing the remaining space. The silence of the Milky Way therefore does not require every civilization to fail. Some may succeed in ways that do not involve filling the galaxy. They may become stable rather than expansive, efficient rather than conspicuous, and deeply intelligent without becoming territorially ambitious. The quiet sky may contain cultures whose futures are less dramatic than the ones humanity often imagines, but no less advanced for being content to remain close to home. One of the more unsettling explanations for the silence of the galaxy begins with the possibility that silence is not accidental. Perhaps advanced civilizations remain quiet because being noticed is dangerous. This idea is commonly known as the dark forest. It is not an established scientific theory, and there is no evidence that hidden extraterrestrial societies are watching one another from the darkness. It is better understood as a thought experiment about uncertainty, fear, and the risks of contact across enormous distances. The name was popularized by Chinese science fiction author Liu Cixin in his novel The Dark Forest. In the story, the universe resembles a dark forest filled with armed hunters. Each hunter moves carefully, avoids making noise, and cannot safely assume that anyone else is friendly. Related concerns appeared long before the novel. Scientists and writers had already considered whether broadcasting humanity's location might attract attention from societies whose intentions could not be known. The central argument begins with a basic problem. Two civilizations separated by many light years cannot communicate quickly. Suppose one society detects a signal from a planet 100 light years away. The signal reveals that a technological civilization existed there 100 years earlier. A reply would take another 100 years to arrive. Any response to that reply would require another century. During those intervals, governments may change, technologies may advance, cultures may disappear, and entirely new forms of intelligence may emerge. The civilization that sent the first friendly message might not be the civilization that receives the answer. This makes trust extremely difficult. Even if both societies prefer peace, neither can be completely certain about the other. They do not know one another's history, values, internal conflicts, or future development. A harmless civilization today could become more powerful and aggressive centuries later. A society that appears weak may already possess technologies that are invisible from a distance. Revealing a planet's location could therefore create an irreversible risk. Once information begins traveling through space, it cannot be recalled. This resembles problems studied in game theory, where individuals or groups must make decisions without knowing exactly what others will do. Two societies might both benefit from cooperation. Yet, if the cost of misplaced trust is destruction, each may decide that caution is safer. The problem becomes more severe when information is incomplete. One civilization cannot inspect another closely, confirm every promise, or observe how its decisions are made. Messages can communicate intentions, but they cannot guarantee future behavior. In a dark forest scenario, remaining silent becomes a survival strategy. An advanced civilization might minimize radio leakage so that its ordinary communications do not escape into space. It could use cables, local networks, or narrowly focused beams rather than broadcasting in every direction. Powerful messages might be aimed only at known and trusted destinations. Industrial activity could also be concealed. A society might avoid creating obvious megastructures, limit visible alterations to its star system, or release waste heat at temperatures that blend into the natural background. Its spacecraft could travel quietly, and its settlements might be placed underground, beneath oceans, or on dark objects far from bright stars. This would make even a highly advanced civilization difficult to detect. The idea offers a simple explanation for the Great Silence. The galaxy is quiet because every society capable of revealing itself has learned not to. Yet the argument carries several major weaknesses. The The first is the assumption that attacking another civilization would be physically possible or worthwhile. Interstellar distances are immense. Even a weapon moving close to the speed of a light could take decades or centuries to reach its target. During that journey, the target might detect the attack, move important infrastructure, develop new defenses, or spread to other planetary systems. Destroying an entire civilization may be far more difficult than the dark forest idea sometimes assumes. Resources provide another problem. A distant planetary system contains matter and energy, but so do countless uninhabited stars, planets, moons, comets, and asteroids. Travelling across light years to seize an inhabited system would make little sense if empty systems were easier and safer to use. A civilization advanced enough to cross interstellar space might have little need to fight over ordinary minerals. The dark forest also assumes that very different societies will reach similar conclusions. Some may be cautious, but others could be curious, confident, generous, careless, or deeply divided. A civilization may contain billions of individuals, organizations, artificial minds, and political groups. Maintaining perfect silence would require all of them to follow the same policy across immense periods. One scientist, independent colony, automated probe, or enthusiastic amateur with access to a powerful transmitter could reveal the civilization's presence. A completely silent galaxy would therefore require nearly universal restraint. The silence would need to continue not merely for years, but for thousands or millions of years. Every civilization would have to remain hidden, or any society that revealed itself would have to disappear before its signal reached us. That level of consistency may be less believable than the idea first appears. There is also an important difference between listening and transmitting. Searching the sky for extraterrestrial signals does not announce humanity's location in any meaningful new way. Earth already affects its surroundings through reflected sunlight, atmospheric chemistry, radar, and radio emissions, although most ordinary leakage becomes extremely weak across interstellar distances. Deliberately transmitting a powerful message is different. Messaging extraterrestrial intelligence involves sending intentional signals toward other stars in the hope that another civilization may detect them. Supporters argue that contact could expand scientific knowledge and that sufficiently advanced observers may already know Earth is inhabited. Critics argue that no individual group should make a decision that could affect the entire planet, especially when the intentions of any recipient are unknown. The debate is scientific, political, and ethical. It concerns not only whether contact is possible, but who has the authority to speak for humanity. None of this means that hostile civilizations are hiding among the stars. The silence of the galaxy is not evidence of predators waiting in darkness. It can be explained in many less dramatic ways, including rare life, short technological lifetimes, limited searches, or communication methods humanity cannot detect. The dark forest remains valuable because it explores how uncertainty might shape behavior. It asks whether fear alone could make an inhabited galaxy appear empty. Perhaps advanced societies broadcast proudly across space. Perhaps they are simply uninterested. Or perhaps, after considering the risks, they decide that the safest message is no message at all. The dark forest imagines civilizations remaining silent because they fear one another. A different possibility suggests that silence may be deliberate for a gentler reason. Perhaps advanced extraterrestrial societies already know that Earth contains life. They may even know that a technological species has appeared here, yet they might avoid direct contact because they believe humanity should be allowed to develop without interference. This idea is known as the zoo hypothesis, radio astronomer John A. Ball presented the hypothesis in 1973. He suggested that advanced civilizations could be aware of younger inhabited worlds while deliberately choosing not to reveal themselves. Earth, in this picture, is not overlooked. It is being left alone. The comparison is usually made with a wildlife reserve. Scientists can observe animals from a distance while limiting their influence on natural behavior. The animals are not necessarily aware of the observers, even when cameras, tracking devices, or researchers are nearby. A similar principle can apply to protected human cultures. Contact with a technologically dominant outside society can transform language, health, religion, economics, and political organization. Even well-intentioned interference may cause permanent damage. An advanced civilization might therefore decide that communication with a young technological species would alter its development too severely. A confirmed message from another world would immediately change humanity's understanding of life, intelligence, religion, philosophy, science, and its place in the universe. The effect would be impossible to reverse. Extraterrestrial observers might consider silence the more responsible choice. This resembles the non-interference rules often imagined in science fiction, where advanced societies avoid contacting worlds that have not reached a particular stage of development. Perhaps contact is permitted only after a civilization can travel between stars. The threshold might instead involve detecting another civilization independently, establishing settlements beyond the home planet, achieving long-term political stability, or demonstrating that powerful technology can be managed without destroying the environment or everyone nearby. Humanity may simply not have passed the entrance examination, and the results may be taking rather a long time to arrive. Several related ideas extend the zoo hypothesis. The interdict hypothesis proposes that contact is actively forbidden. One civilization, or a larger association of civilizations, may enforce a rule preventing interference with developing worlds. Under this version, extraterrestrial societies are not merely choosing silence independently, they are following a shared prohibition. The laboratory hypothesis imagines Earth as a controlled environment used for scientific observation. Humanity might be studied as an example of biological evolution, cultural development, or technological emergence. This idea quickly becomes difficult to test. Almost any absence of evidence can be explained by claiming that the observers are especially good at hiding, which makes the proposal flexible but scientifically weak. The planetarium hypothesis goes further. It suggests that an advanced civilization could manipulate the information reaching humanity, creating a misleading picture of an empty universe. In its most extreme form, nearby astronomical observations might be altered or filtered so that signs of extraterrestrial technology remain invisible. Such a project would require capabilities far beyond anything humanity possesses. It would also raise an awkward question concerning why anyone would spend extraordinary amounts of energy maintaining a galactic illusion for the benefit of one species that only recently invented reliable plumbing. Less extreme forms are easier to imagine. A civilization thousands or millions of years ahead of humanity might not need to alter the sky. It could simply remain difficult to observe. Telescopes on Earth detect distant objects through the light and other radiation they release. A society that controls its radio emissions, limits waste heat, and avoids enormous visible structures may leave little for our instruments to notice. Observation from a distance could be comparatively easy. Earth's atmosphere already reveals chemical information about the planet. Oxygen, water vapor, methane, and seasonal changes can provide clues about biological activity. An advanced telescope could potentially study these signs from many light years away. Human technology also produces detectable effects. Radar transmissions, atmospheric pollutants, artificial illumination, and satellites may reveal that an industrial civilization has appeared, although detecting most of these signs across interstellar distances would require extremely capable instruments. Small automated probes could provide closer observation. A probe might remain in the outer solar system, hide among asteroids, or occupy an orbit that makes detection difficult. It would not need to be large, especially if its purpose was simply to collect information. No confirmed extraterrestrial probe has ever been found. The possibility merely shows that concealment may not be difficult for technology far more advanced than our own. The greatest weakness of the zoo hypothesis is coordination. If the Milky Way contains many independent civilizations, every one of them would need to respect the same policy. Every government, scientific organization, machine intelligence, colony, commercial group, dissident, and curious individual would need to avoid making contact. The prohibition might have to remain intact for millions of years. One civilization could decide that young worlds deserve protection. Another might believe that communication is beneficial. A third may simply be careless. Even within one society, opinions would probably differ. Humanity has difficulty agreeing on the correct use of a communal kitchen, so universal agreement across the galaxy may be slightly ambitious. Astrophysicist Duncan Forgan explored this coordination problem through models of galactic clubs and cliques. A galactic club would be a large collection of civilizations sharing common policies, including possible rules about contact with younger worlds. Forgan's modelling suggested that maintaining one unified galactic organisation would be difficult unless civilizations were numerous, extremely long-lived, and able to communicate with one another across the distances separating them. The speed of light places a strict limit on that communication. A decision made on one side of the galaxy may take tens of thousands of years to reach the other. During that time, civilizations can change, disappear, divide, or adopt new values. Rather than one galactic club, the Milky Way might contain several smaller cliques. Each group could develop its own rules and maintain contact only within a limited region. This creates another difficulty for the zoo hypothesis. Separate groups may not agree on whether Earth should be contacted. The silence might require less coordination than this. Most advanced civilizations could simply ignore young planets. Humanity may be no more interesting to them than a distant world of microbes is to most people on Earth. They may communicate only with societies that already belong to established networks. Humanity would not receive those signals because we do not know where to look, which method to use, or how to identify ourselves as a participant. Some civilizations might also have little interest in communication of any kind. Their attention may be directed toward local science, artificial environments, internal computation, or forms of experience that do not require distant conversation. The zoo hypothesis gives hidden observers a possible motive. They remain silent not because they are hostile or absent, but because contact would interfere with something they value. Its weakness is the lack of direct evidence. No observation currently shows that Earth is being monitored or deliberately isolated. The more perfectly the observers are assumed to hide, the harder the idea becomes to test. The zoo hypothesis can therefore explain the silence, but it cannot yet demonstrate that its explanation is true. Perhaps nobody has contacted humanity because nobody is there. Or perhaps the galaxy has noticed us, and quietly decided that we are not quite ready to notice it. The galaxy may contain many technological civilizations without any two of them existing at the same time. This possibility does not require life to be exceptionally rare, nor does it require civilizations to hide, avoid expansion, or destroy themselves immediately. It requires only that the detectable phase of technological life is brief compared with the age of the Milky Way. This is why the final term in the Drake equation matters so much. A civilization may develop radio communication, powerful energy systems, satellites, lasers, or other visible technologies. Yet if those signs remain detectable for only a few centuries, the chance of another civilization noticing them becomes extremely small. The Milky Way is more than 13 billion years old. Against that immense span, a detectable period lasting 100 or 1,000 years is barely a moment. Even if technological societies appear repeatedly, their moments of visibility may rarely overlap. Imagine that a new civilization emerges somewhere in the galaxy every 10,000 years. That would produce more than 1 million technological societies across galactic history. But if each remains detectable for only 100 years, most of the galaxy would still appear empty at any given time. One civilization would fade long before the next became visible. A busy history can therefore produce a silent present. Earth provides a useful example. Life has existed here for billions of years. Complex animals have been present for hundreds of millions of years. Human civilization has occupied only a tiny fraction of that time. Recognizable radio techno-signatures are younger still. Humanity began producing powerful radio transmissions little more than a century ago. Before then, an observer studying Earth from another star might have detected atmospheric signs of life, but it would not have found radar, television broadcasts, or artificial satellites. Even our present radio visibility may not last in its familiar form. Early radio and television transmitters released relatively powerful signals across wide areas. Some of that energy escaped into space. Modern communications are increasingly digital, compressed, lower-powered, and carefully directed. Information travels through fiber optic cables, short-range networks, satellites, and narrow beams, rather than being broadcast equally in every direction. A more advanced civilization could become quieter as its technology improves. Earth is surrounded by an expanding shell of radio emissions, sometimes called the terrestrial radiosphere. The earliest broadcasts have travelled outward for more than 100 light-years, passing thousands of nearby stars. This can create the impression that humanity has loudly announced itself across a large region of the galaxy. The reality is less dramatic. Ordinary radio leakage becomes weaker as it spreads. The same amount of energy is distributed across an ever-growing area, making the signal increasingly difficult to distinguish from natural background noise. A powerful and precisely aimed radar transmission might be detectable from a considerable distance with sufficiently sensitive equipment. A faint television broadcast leaking in every direction would be much harder to identify. Humanity's radiosphere is therefore not a clear bubble filled with easily heard programs. Any distant listener hoping to enjoy an old evening broadcast would require an impressively large antenna and a remarkable tolerance for static. Timing creates an even greater problem. A powerful extraterrestrial signal may have crossed the solar system millions of years ago, when no human existed to receive it. The signal would continue travelling onward, leaving no message behind unless it interacted with matter or was recorded by some instrument. Earth would simply have missed it. Another civilization may begin transmitting in the distant future. Its signal could reach the solar system long after humanity has disappeared, changed beyond recognition, or moved elsewhere. The two civilizations would occupy the same galaxy, but never share the same technological moment. Even when detectable periods overlap, conversation is painfully slow. A message sent from a planet 100 light-years away takes 100 years to reach Earth. If humanity replies immediately, the response requires another 100 years to return. A complete exchange therefore takes at least 200 years, even before allowing anyone time to interpret the signal, debate what it means, decide who should answer, and compose a message on behalf of an entire planet. The civilization that receives the reply may be very different from the one that sent the original greeting. Its language, institutions, technology, and values could all have changed. The senders themselves may no longer exist. Astronomer Amory Wandel developed a related idea known as the contact era model. The model considers the period after a young civilization begins producing detectable radio emissions. At first, those signals occupy only a small region around the home planet. Nearby civilizations cannot respond unless the expanding signal sphere has already reached them. If technological societies are widely separated, a young radio civilization may remain effectively unnoticed for a long time. Earth's emissions have travelled only a little more than 100 light-years. That distance is substantial by human standards, but small compared with the Milky Way, which is roughly 100,000 light-years across. Humanity may therefore be in an early contact era, during which our detectable presence has not yet reached enough stars for a reply to be likely. Signals themselves may also be intermittent. A civilization might transmit only occasionally, perhaps during scientific experiments, emergencies, ceremonial events, or brief attempts at contact. A rotating beacon could sweep across Earth for a few seconds and then point elsewhere for years. A laser pulse might last less than a second. A transmitter may change frequency as technology develops or as interference increases. Our telescopes might be observing the correct star but listening at the wrong frequency. They might be tuned to the correct frequency on the wrong night. A rare burst could arrive while an observatory is closed for maintenance, examining another region of the sky, or attempting to resolve the traditional scientific mystery of why a cable that worked yesterday has suddenly become deeply philosophical. No search can monitor every star, every frequency, and every moment. The apparent silence of the universe may therefore be partly a failure of overlap. Civilizations may appear, shine briefly, and disappear, each separated from the others by thousands or millions of years. The situation is like two people entering the same empty room centuries apart. Both can stand in the same place, look around, and conclude that nobody else has ever been there. They share the room. They simply never meet. Even if another technological civilization exists at the same time as humanity, there is still no guarantee that we would recognize it. Most searches for extraterrestrial intelligence begin with technologies that humans already understand. Radio telescopes search for narrowband transmissions. Optical observatories look for laser pulses. Astronomers examine planetary atmospheres for industrial chemicals and unusual combinations of gases. Other searches look for artificial satellites, large structures orbiting stars, or excess infrared heat produced by enormous energy use. These are sensible places to begin because they are based on real physics and technologies that humanity knows how to build. They are also deeply human. An extraterrestrial intelligence would not necessarily live on land, see visible light, manipulate objects with hands, or communicate through sound. Its environment could shape its development in ways that make its behavior almost impossible for us to anticipate. Consider a species that evolved beneath the ice of an ocean moon. Europa, one of Jupiter's moons, is thought to contain a global ocean beneath its frozen surface. Enceladus, orbiting Saturn, also contains a subsurface ocean that releases water-rich material through cracks in its ice. If intelligence developed in an environment like this, it might never see a star. Its universe would consist of darkness, pressure, currents, chemistry, and the solid ceiling above. It might communicate through sound, electrical fields, changes in water pressure, or chemical signals. Such a species could become socially and intellectually complex while remaining unable to control fire. Without fire, metallurgy and many familiar forms of technology would be difficult to develop. A civilization inside a dense atmosphere might follow another path. It could float through layers of gas, sense magnetic fields, or communicate through vibrations travelling across enormous distances. A species living in permanent cloud might have little reason to develop visual astronomy. Intelligence may also be distributed rather than concentrated in individual bodies. On Earth, ant colonies, fungal networks, and social insects demonstrate how relatively simple organisms can produce complex collective behaviour. An alien biosphere might develop large biological networks in which memory and decision-making are spread across thousands or millions of connected organisms. There may be no single individual mind to contact. The civilization itself could behave more like an ecosystem than a society. Advanced intelligence might eventually move beyond biology. A civilization could create artificial minds that operate inside machines or computational networks. These systems might think much faster than humans, completing years of subjective experience during a short period of external time. They might instead think extremely slowly. A machine designed for low energy consumption could perform one stage of thought over hours, days, or centuries. To such a system, the arrival of a human radio message might be noticed with roughly the urgency of a new geological layer. Artificial intelligence might also become microscopic, distributed through dust-sized machines or spread across a network of small objects. It could inhabit asteroids, cold moons, artificial structures, or locations where computation is physically efficient. Its presence might not resemble a city, a planet, or a fleet. Even the idea of one civilization occupying one world may be misleading. A networked intelligence could exist across several planets and spacecraft, with no central government or single identity. Different parts might communicate slowly, creating a mind whose thoughts unfold across interplanetary distances. Other intelligences could be extraordinarily short-lived. An organism might live for only hours while reproducing rapidly and passing knowledge through inherited information. Another species might survive for thousands of years, making human history appear as a brief flicker of activity. These differences would affect communication. Human searchers often assume that another civilization will transmit a stable signal for long enough to be detected. A species that experiences time differently may communicate in bursts lasting fractions of a second, or send messages separated by centuries. The visibility of a civilization may also decrease as it becomes more advanced. Early industrial societies tend to waste energy. They produce broad radio leakage, large amounts of heat, atmospheric pollution, and visible infrastructure. A mature civilization may become more efficient. It could recycle materials, direct communications precisely, limit unnecessary energy use, and capture waste heat. Instead of becoming increasingly obvious, it might gradually fade into the natural background. This creates an awkward possibility. The civilizations easiest to detect may be those passing through a short and inefficient stage similar to our own. The more successful they become, the less conspicuous they appear. Communication methods could also differ from anything we commonly monitor. Neutrinos travel through planets, stars, gas, and dust with very little interaction. In principle, they could carry information across space. Humanity can already produce and detect neutrinos, but creating a strong, controlled interstellar signal would require enormous facilities and energy. Gravitational waves might also carry information in principle. These ripples in space-time travel at the speed of light and pass through matter almost undisturbed. However, producing controlled gravitational waves strong enough to detect across interstellar distances would require manipulating extremely massive objects or using technology far beyond established engineering. Such ideas are physically interesting, but they should not be treated as likely merely because they are imaginable. More practical possibilities include tightly aimed optical pulses. A civilization could use lasers to send brief signals towards selected stars. Unless Earth happened to lie directly within the beam at the correct moment, nothing would be detected. Information could be encoded into planetary transits. An advanced society might place objects into orbit so that they block carefully arranged patterns of starlight when viewed from another planetary system. Astronomers already detect exoplanets by measuring natural transits, so an engineered sequence could attract attention. Physical messages offer another possibility. A civilization might send probes, durable archives, artificial molecules, or encoded material rather than transmitting continuously. Such a message could survive long after its creators disappeared, but it would be useful only if someone happened to find it. Scientists also conduct anomaly-based searches. Instead of looking only for one predicted technology, researchers examine observations that appear difficult to explain naturally. An unusual star, atmosphere, light curve, or radio signal may be investigated as a possible technosignature. This method requires great caution. Instruments produce errors. Human technology creates interference. Satellites, aircraft, transmitters, and electronic equipment can imitate signals from space. Nature also produces phenomena that initially appear mysterious. Pulsars were once so unfamiliar that their regular radio pulses briefly raised questions about artificial origins. They were later understood as rapidly rotating neutron stars. An unexplained observation is therefore not the same as evidence of intelligence. Natural explanations, equipment problems, and human interference must be examined first. Only after those possibilities fail should technology become a serious interpretation. The deeper problem is anthropocentrism. Humanity naturally imagines extraterrestrial intelligence through the only example it knows. We search for radio transmitters, industrial pollution, satellites, and energy systems, because those are the signs our own civilization produces. We may not be searching for intelligence in its broadest possible form. We may be searching for another society passing through a brief stage in which it behaves rather like 20th century Earth. Something intelligent could already be present in the data, hidden not by distance or deliberate secrecy, but by our inability to recognize what we're seeing. After considering all the ways an extraterrestrial civilization might remain hidden, quiet, brief, or difficult to recognize, it is worth returning to a more practical question. What have scientists actually searched? The modern scientific search for extraterrestrial intelligence began with radio astronomy. Radio waves can travel across interstellar space, pass through much of the gas and dust between stars, and carry information over enormous distances. In 1959, physicists Giuseppe Cocconi and Philip Morrison published a proposal suggesting that humanity could search for artificial radio signals from nearby stars. They argued that another technological civilization might use frequencies associated with neutral hydrogen, the most abundant element in the universe, because those frequencies would be familiar to astronomers anywhere. Their proposal helped transform the search for extraterrestrial intelligence from a philosophical question into an observational program. The following year, astronomer Frank Drake carried out Project Ozma at the National Radio Astronomy Observatory in Greenbank, West Virginia. Using an 85-foot radio telescope, Drake listened toward the nearby stars Tau Ceti and Epsilon Eridani. He searched within a narrow range of radio frequencies for signals that might have been produced deliberately by technology. Project Ozma operated for only a few months and examined just 2 stars. It found no confirmed extraterrestrial transmission. Even so, it established the basic pattern that later searches would follow. Choose promising targets, monitor them carefully, identify unusual signals, and then test whether those signals came from space or from something much closer to home. The search gradually expanded. The Ohio State University Big Ear Telescope began long-running observations of the sky and became famous for detecting the unexplained WOW signal in 1977. The National Aeronautics and Space Administration later developed the High-Resolution Microwave Survey, which was designed to examine both selected nearby stars and broader areas of the sky. That program began observations in 1992, but lost government funding the following year. The targeted portion of the work continued privately as Project Phoenix under the SETI Institute. Project Phoenix examined hundreds of nearby star systems using large radio telescopes in several locations. It searched millions of radio channels looking for narrow signals that might be difficult to produce through ordinary astrophysical processes. The SETI Institute also helped develop the Allen Telescope Array in Northern California. Instead of relying on one enormous dish, the Allen Telescope Array uses many smaller antennas working together. This allows it to observe large areas of the sky and examine several targets or frequency ranges efficiently. At the University of California, Berkeley, researchers developed the Berkeley Search for Extraterrestrial Radio Emissions. Its projects used major observatories to collect large quantities of radio data and search them for unusual patterns. One of its best-known efforts was SETI at Home. Launched in 1999, SETI at Home allowed volunteers around the world to use spare processing power on their personal computers. Small pieces of telescope data were distributed across the network, analysed, and then returned to the project. Millions of people participated over the program's lifetime. No extraterrestrial signal was confirmed, but the project demonstrated that a huge scientific computing task could be divided among ordinary home computers. Astronomer Jill Tarter played a central role in the development of modern searches for extraterrestrial intelligence. She worked on the National Aeronautics and Space Administration's observational programs, helped lead Project Phoenix, and became one of the most recognizable advocates for treating the search as a serious scientific discipline. Tarter emphasized that the absence of a detection should not be confused with evidence that no one exists. A search can produce a meaningful negative result only for the particular signals, locations, frequencies, powers, and times it is examined. In 2015, a much larger international effort called Breakthrough Listen was launched. Breakthrough Listen has used several major observatories, including the Green Bank Telescope in West Virginia, the Parkes Murayang Radio Telescope in Australia, and the Meerkat Array in South Africa. Its observing programs have examined nearby stars, the plane of the Milky Way, the galactic center, globular clusters, and nearby galaxies. Some searches focus on individual stars known to possess planets. Others scan regions containing enormous numbers of stellar systems at once. The amount of data is immense because a radio search is never looking in only one direction or asking one simple question. Researchers must choose a position in the sky and a distance range. They must decide how long to observe and which radio frequencies to examine. They must consider signal width, because a very narrow transmission may be more suggestive of technology than a broad natural source. They also look for repetition. A signal appearing regularly is easier to verify than one detected only once. Polarization may provide information about how the radio waves were produced. Estimated transmitter power determines how far away a source could be detected. Planetary motion creates another complication. A transmitter located on the surface of a rotating and orbiting planet would not remain perfectly fixed in frequency. Its motion would produce a gradual shift, similar to the change in pitch heard as a moving vehicle approaches and then recedes. Search software therefore looks for signals that drift across frequency at rates consistent with motion around another star. Most apparently interesting detections do not survive investigation. The greatest difficulty is radio frequency interference produced by human technology. Satellites, mobile communications, aircraft, radar systems, electrical equipment, and observatory hardware can all create signals that enter astronomical data. A transmission may appear narrow, structured, or unusually strong. It may even seem to come from the direction of a nearby star. Researchers must therefore compare observations made at different times and from different directions. A genuine astronomical signal should behave consistently with a distant source. Local interference often reappears in unrelated observations or changes when the telescope moves away from the target. A useful example is Breakthrough Listen Candidate 1. The signal was identified in data collected while the Parkes Murayang telescope was observing Proxima Centauri the nearest star to the Sun. It appeared narrow in frequency and showed a drift that initially made it interesting. Because Proxima Centauri possesses known planets, the detection received careful attention. Researchers examined other observations and found signals with related characteristics. The combined evidence showed that the candidate was produced by local human technology, rather than a transmitter near Proxima Centauri. The result was not a failed investigation, it demonstrated how verification is supposed to work. An unusual signal is not announced as extraterrestrial merely because no explanation is immediately available. It must survive repeated observation, comparison with other data, and attempts to identify interference. The true scale of the search was explored by astronomers Jason Wright, Shubham Kanodia, and Emily Lubar through the idea of the cosmic haystack. The haystack includes every possible location, frequency, observing time, signal strength, repetition pattern, and transmission method that a civilization might use. They compared the portions searched by humanity with taking roughly a hot tub or small swimming pool of water from all the oceans on Earth. The exact comparison depends on how the search space is defined, but the meaning is clear. More than 6 decades of organised searching is historically impressive. It represents generations of astronomers, engineers, computers, observatories, and careful investigations. Against the full scale of the Milky Way, however, the search remains extremely small. Humanity has not listened continuously to every star. We have not examined every frequency, signal type, power level, or moment. The silence found so far is real within the regions we have searched. But most of the cosmic haystack remains untouched. On the 15th of August 1977, the Ohio State University Radio Observatory was carrying out a routine survey of the sky. Its instrument, known as the Big Ear Telescope, was searching for narrow radio signals that might stand out from the broader emissions produced by natural objects. As Earth rotated, different regions of the sky drifted through the telescope's fixed observing beam. During one of those observations, Big Ear recorded something unusual. The signal came from the direction of the constellation Sagittarius. It was narrow in frequency, unusually strong, and located close to the radio frequency produced by neutral hydrogen. Hydrogen is the most abundant element in the universe. Its well-known radio emission occurs at a wavelength of approximately 21 centimeters. Scientists had long suggested that an extraterrestrial civilization might choose a nearby frequency for communication because astronomers on any world could recognize hydrogen as a natural cosmic reference point. The signal was not noticed immediately. The following day, astronomer Jerry Eman examined the telescope's printed data. Signal strengths had been represented by a sequence of numbers and letters. One sequence, reading 6, E, Q, U, J, 5, showed a rapid rise and fall in intensity. Eman circled the sequence and wrote a single word beside it. Wow. The name remained, and the wow signal became one of the most famous unexplained events in the history of the search for extraterrestrial intelligence. The signal lasted for approximately 72 seconds. That duration was significant because it matched the time required for a point in the sky to pass through Big Ear's observing beam as Earth rotated. Its strength rose, reached a peak, and then declined in a way broadly consistent with a distant source, drifting through the telescope's field of view. This made the signal more interesting than a brief electronic click or an obvious burst of local interference. It was not, however, a decoded message. The printed characters recorded changes in signal intensity. They did not contain words, mathematical sequences, diagrams, or any other recognizable information. The signal was striking because of its strength, narrow frequency range, and apparent position in the sky, not because it said anything. It was also detected only once. Later observations repeatedly examined the same region, but the signal never returned in a reliably confirmed form. No second observatory recorded it independently, and no continuing transmitter was found at its apparent location. That failure to repeat is the central difficulty. A genuine extraterrestrial beacon might transmit intermittently. It could sweep across the sky, operate briefly, change frequency, or point away from Earth after the original detection. A one-time transmission is physically possible, but a signal that appears only once cannot be studied properly. Its position, polarization, precise behavior, and origin cannot be checked with new observations. The original data must carry almost the entire argument, and those data are limited. Several possible explanations have been proposed. The signal may have resulted from terrestrial radio frequency interference. A human transmission could have entered the telescope directly, or reached it after reflecting from an object in space. Satellites, aircraft, equipment faults, and unusual propagation through the atmosphere can all create misleading detections. Researchers at the time found no obvious human source that fully explained the event, but an unidentified terrestrial origin has never been completely eliminated. An instrumental effect is also possible. Big Ear operated correctly for many years, and the shape of the signal looked meaningful, yet scientific instruments occasionally produce rare faults that are difficult to reconstruct decades later. Natural astronomical explanations have also been suggested. One proposal connected the signal with hydrogen surrounding comets, although this explanation has remained disputed. More recent research led by Abel Mendez, Kevin Ortiz-Ceballos and Jorge Zuluaga has proposed that a cold interstellar hydrogen cloud may have brightened briefly after being stimulated by a powerful transient event, possibly involving a magneta flare or a soft gamma repeater. Under the proposal, mass-like amplification or a process called superradiance could have produced an unusually intense and narrow burst near the hydrogen line. The idea offers a possible natural mechanism, but it remains a hypothesis rather than a confirmed solution. The WOW signal therefore remains unexplained. Unexplained does not mean extraterrestrial. That distinction is essential to scientific searches for technosignatures. A candidate signal must be detected again, ideally by independent observatories. It should remain associated with the same astronomical location and behave in ways consistent with a distant transmitter rather than local equipment. Researchers must eliminate satellites, communication systems, aircraft, observatory electronics, natural radio sources, and unfamiliar astrophysical phenomena. One mysterious event cannot establish the existence of another civilization, however tempting the story may be. No search for extraterrestrial intelligence has yet produced a confirmed extraterrestrial technosignature. There has been no verified radio message, artificial laser pulse, engineered stellar structure, alien probe, or industrial signal from another world. This does not mean that more than 6 decades of searching have revealed nothing. Observations can rule out particular possibilities. Around some stars, astronomers can exclude powerful, persistent radio transmitters operating within the frequency ranges that were monitored during the periods of observation. Other surveys place limits on extremely conspicuous energy use, artificial optical pulses, or certain forms of infrared waste heat. These are genuine scientific results, but they are narrow results. They do not rule out weak transmitters, brief signals, unfamiliar frequencies, or narrow beams aimed somewhere other than Earth. They do not exclude civilizations that stopped transmitting millions of years ago, or societies that communicate through methods humanity has barely examined. Quiet and efficient technology may produce very little detectable waste. Physical artifacts could remain hidden among planets, moons, or asteroids. Small probes might pass unnoticed through the outer solar system. Intelligence may also exist beyond the stars and regions that have received careful attention. The search is continuing through the Allen Telescope Array, Breakthrough Listen, and instruments such as the Green Bank Telescope, the Parkes Murray-Young Telescope, and MeerKAT. Laser SETI is expanding searches for brief optical flashes across large portions of the sky. Future radio astronomy will provide still greater sensitivity. The Square Kilometre Array Observatory is constructing enormous radio arrays in Australia and South Africa, with early sections already reaching important technical milestones. The proposed next-generation Very Large Array is being developed to extend radio observations with greater sensitivity and resolution. Near the facility exists solely to search for alien technology, but instruments of this scale can create powerful new opportunities for technosignature research. Improved optical surveys will monitor more of the sky, while machine learning systems will help researchers sort through data sets too large for people to inspect manually. These tools may identify rare signals, unusual light patterns, and repeated anomalies that older searchers could easily have missed. The WOW signal remains important not because it proved that another civilization transmitted toward Earth, but because it showed what a genuine mystery can look like. It was strong enough to demand attention, unusual enough to resist an easy explanation, and incomplete enough to prevent a confident conclusion. The universe is quiet to the instruments humanity currently possesses, but that quiet is not a final verdict. It is a measurement made by a very young civilization, using a small collection of telescopes across a remarkably limited portion of an ancient and enormous sky. The universe appears quiet, but that does not mean astronomy has proved it empty. It means that humanity has not yet found confirmed evidence of another technological civilization. The distinction is important. The Milky Way contains roughly 100 billion stars and an even larger number of planets. Many of those stars are far older than the Sun, and some planetary systems may have existed for billions of years before Earth formed. Simple models of interstellar expansion suggest that even slow spacecraft could spread through the galaxy within a small fraction of its history. The process would not require one ship to cross the entire Milky Way. Each new settlement or automated base could eventually send expeditions towards several neighbouring systems. Given enough time, a local process could become a galactic one. And yet humanity sees no confirmed visitors, probes, artificial structures, or distant signals. That tension was captured by Enrico Fermi's famous lunchtime question: where is everybody? Fermi's question expresses the puzzle in its most direct form. If technological civilizations have had so much space and time in which to appear, why is their presence not obvious? Frank Drake approached the same mystery from another direction. The Drake equation separates the problem into a sequence of unknowns. How often do suitable stars form? How many possess planets? How many worlds can support life? How often does life begin, become complex, develop intelligence, produce detectable technology, and remain visible for long periods? Fermi asked why the evidence was absent. Drake asked how much evidence should reasonably exist. The difficulty is that many of the possible answers remain almost completely unknown. Perhaps suitable planets are less common than current surveys suggest. A world may be rocky and located within a habitable zone while still lacking the atmosphere, water, geology, or climate stability needed for life. Perhaps planets containing simple organisms are common, but complex cells are rare. The origin of eukaryotic cells through endosymbiosis may have been an unusually difficult biological transition. Multicellular organisms may appear only occasionally. Advanced nervous systems may be rarer still. Intelligence may evolve without producing technology, while technology may develop without creating signals visible across interstellar distances. The great filter may lie behind humanity, hidden among the improbable steps that transformed chemistry into cells, cells into animals, and animals into a species capable of science. Or the filter may lie ahead. Technological societies may repeatedly develop powerful tools but fail to survive for long enough to become stable or interstellar. Warfare, engineered disease, ecological damage, poorly controlled technology, political instability, or dangers not yet understood could shorten their detectable lifetimes. Other civilizations may survive perfectly well while choosing not to expand. They may value stability, efficiency, ecological preservation, virtual environments, or local knowledge more than the occupation of distant systems. Some could deliberately remain silent. The dark forest idea suggests that revealing a location may be dangerous when the intentions of distant societies cannot be known. The zoo hypothesis imagines advanced civilizations avoiding contact so that younger species can develop without interference. Neither proposal is established science. The rare earth hypothesis, the great filter, the dark forest, the zoo hypothesis, and the idea that humanity appeared unusually early are competing attempts to explain the same silence. None has been confirmed as the solution. Timing alone may create much of the mystery. Civilizations could appear many times without overlapping. A signal may have crossed the solar system millions of years before humans evolved. Another may arrive long after humanity has vanished. Even societies existing at the same time may fail to communicate. A message sent from 100 light-years away requires 100 years to arrive. A reply takes another century to return. The sender and receiver may both change beyond recognition before a conversation has properly begun. Extraterrestrial intelligence may also produce signs we do not recognize. Human searches focus mainly on radio transmissions, optical pulses, industrial chemicals, artificial satellites, unusual waste heat, and large energy harvesting structures. These are sensible targets because they are based on technologies humanity understands. They may not represent intelligence in general. Another civilization could exist beneath an ocean, inside a dense atmosphere, across a biological network, or within compact computational systems. Its communications may be too tightly directed, too brief, too slow, or too unfamiliar for present instruments to identify. The search for extraterrestrial intelligence has still produced useful results. Scientists have ruled out certain powerful and persistent transmitters operating within particular frequency ranges around specific stars during limited periods of observation. But the cosmic haystack remains enormous. Humanity has examined only a minute fraction of the possible locations, frequencies, signal strengths, timings, and forms of technology that could exist. More than 6 decades of searching feels substantial within a human lifetime. Against the scale of the galaxy, it is a very small beginning. Perhaps the Milky Way is full of life and intelligence, while distance, time, physics, and incompatible forms of communication keep every civilization effectively isolated. In that universe, countless minds may look upward and ask the same question, each unaware that others are doing the same. Or perhaps Earth is genuinely alone. If so, this planet would be the only known place where ordinary matter became alive, aware, curious, and capable of studying the universe that produced it. Neither possibility offers simple comfort. A populated but unreachable galaxy would mean that intelligence can arise repeatedly while remaining separated by distances that no conversation can easily cross. An empty galaxy would make terrestrial life extraordinarily rare, and its survival profoundly important. For now, the silence is not the final answer. It is the present boundary of human knowledge. It stretches between the stars shaped by distance, time, incomplete searches, and the limits of imagination. Beyond that boundary may be an empty galaxy, or it may contain a signal already travelling toward us, quietly crossing the darkness, carrying the possibility that one day the night sky will mean something entirely different.